first thing was, well, we need a way of managing it. So our first solution was, well, when you hit block 10,001,
You compress it?
no, you just delete block 1.
Okay.
And block 2 now is your Genesis block,
Yeah.
right? And that was actually, we'd be chatting with people and they're like, oh, but you can't do that. I'm like, well, why can't you do that?
Yeah, you can.
You can. The problems are, some people like, it was mostly ideological, where people like, well, you need it. And we're like, well, tell us why you need it. And they go, well, you need it because your money will disappear. But
no, that's a Bitcoin.
Well, no, that's
the Bitcoin peak.
I'm walking you to something better. And we're like, well, if your money disappears, what you want to do is you want to manually send it to
Another account. Yeah.
Right, like as soon as you rebroadcast, your money's still there.
There's a blockchain that does exactly that. Like you have pretty much all your UTXOs get cleaned up.
Yeah.
Like it's not about blockchain, it's just literally your UTXO table get cleaned up. So if you want to keep your money, you need to resend them.
What's
like
the name? Look it up for us because we got something.
This is one of the key problems of being in a seniorish role in a blockchain project is the sheer mental effort of remembering all the other projects and what they do.
There's some things that use ZK snarks. One of the problems is they're only dealing with, most of them that I've seen, they're only dealing with tokens or data. So they'll like regenerate a ZK snark or whatever, and then they'll be able to delete the stuff. But I mean, if you've got it on this, the solution is actually this. The solution is, okay, you can rebroadcast if you want. But when block 10,001 is produced, everybody knows that block 1 is going away. So you automatically reformat and rebroadcast the transactions with a consensus layer mediating not only the rebroadcast, but also a rebroadcasted fee. And you do this so you don't only broadcast the UTXO data, but you rebroadcast the data that's affixed to the transaction as well. So this solves a lot of really interesting problems because the transaction fee, let's make this, what we do at Saito is we make it 2 times the average fee of new transactions. And something really wonderful happens. You can have a blockchain of like a fixed size. So you can say like it's 1 gigabyte block. Now, as the data on the chain grows, there's less and less space available for new transactions, right? So the new transactions start getting crowded out by the old transactions because you have to rebroadcast the old. If you don't rebroadcast every single transaction, no one else on the network treats that block as valid. So, you know, you could have people attacking the network, but it would be a 51% attack, right? And you could do it in Bitcoin anyway. You fork and remove Satoshi's coins. The really interesting thing is the space for new blocks shrinks, the fees for new blocks go up. As the fees for new blocks go up, the fees for old blocks go up more. You've got an incentive now for people to manually rebroadcast 1. But second of all, what you move is you move towards an equilibrium where the price of new transactions and the price of old transactions moves into equilibrium, and the amount of new data that goes onto the blockchain is the same as the amount of old data that's purged from it. And we finally have an economic solution to blockchain scaling and chain management because not only does the blockchain stay at a certain size, but it stays at a certain size where you can guarantee that the data that's attached to your transaction will stay on the chain. So if you want your stuff on the blockchain forever, you can actually pay for it. If you just want your stuff falling off because you want a universal broadcast feature, you pay a much lower fee because you don't need to pay every loop. And something else happens. There's a lot of cheating in Bitcoin where the miners, for instance, like you pay your fee, there's no guarantee that the people managing the chain will keep the data. All they really need to do is maintain the UTXO set. So right, so they purge the data, or there's no guarantee that they need to sync it to anyone else.
Why do you need transaction data in the first place?
Because we want to use a blockchain for more than money.
I mean, like, we use blockchain for more than money without having any transaction data stored.
Think op return.
What?
When I say transaction data, I'm talking about op return. Stuff you would stick in the op return field.
So that's what I'm saying. Like we don't store that, and you can use blockchain for any like incomplete stuff, right? Like the way just to explain, like I think of blockchain as a database which has a transaction log. And the transaction log really you need like on the head of it, and you can forget about the So yeah, there's transaction data. It's just like really you need it only for some period of time. Your database is where you should store your shit.
Well, one, we think of a blockchain as a universal propagation network. So there are applications where you want the op-return stuff to broadcast.
Yeah.
And most blockchains, because they don't have this problem solved, they go to this position where it's like, well, the data you archive, you store it yourself.
Yeah.
There are situations where, well, you're paying to use the blockchain, so you don't want to use that. You actually want data stored on the blockchain. For instance, something like a commercial insurance project. You want to keep the data on chain for 3 years because that's your length of legal liability. I mean, you could maintain your own servers, but if you're maintaining your own servers, you don't actually need a blockchain for this.
Yeah. But like, why don't you store it as a part of state? Like that's what I'm saying. Like you storing it as part of transaction data. I'm saying just store everything as part of state.
There's no reason you can't do that too. But
then you don't need transaction data. Then you can purge this without any problems.
that's like saying an airplane doesn't need drink service. An airplane doesn't need drink service, but it's better if it has drink service. So if you have drink service, you can provide some kind of services that if you don't have drink services, you're not able to do, like move sports teams, right? So, this is a solution.
Yeah.
And for some use cases, this is better than that, right? Because this is expensive because it's actually using the blockchain for a certain kind of storage.
Yeah.
On the other hand, it's guaranteeing certain properties of that transaction stick around. Like there are some things like, let's say I've got a name card.
Yeah.
And that name card has a bunch of stuff on it, like this is my PGP key, this URL here is where you're going to fetch my distributed Facebook posts. You could take that name card and you could have the name card circling along. Now, if at moment of broadcast somebody needs to stick it in a database, a user can't come along 2 years later and then collect it because, well, no one's got it. And you've got a coordination problem. This is the BSV MongoDB problem. They introduce massive coordination problems because they're like, okay, you're going to negotiate separately with Unwriter. He's going to save the data for you if you pay for it. And all of a sudden, like you're using a blockchain, but all of the users need to coordinate on which access point to use. They all need to have a second layer economic situation. With this, everything is paid for by the fee. So the coordination issues are solved because every node on the network must have the data. All you've got to do is convince someone to give you access to the blockchain and you've got it. But it's for a subset of use cases. It's not, for most use cases, like if you've got a signed message from someone, stick it in the database. Then you pay a lower fee and you don't need to be paying to keep it on the chain.
Well, actually, the way you're actually paying for keep it on the database, like you're paying the rent.
Well, you've got to pay your own. Yeah, the rebroadcast fee is going to be more expensive than sticking it in a private database.
No, it's not private. That's the shared database that, as part of the consensus is maintained. That's what I'm saying.
Well, that's the blockchain.
It is a blockchain. Yeah. But that's what I'm saying. Like the way I look at blockchain is a database with the way you synchronize between masters and slaves is by sending around transaction log.
I mean, I see.
That's why the transaction log actually doesn't matter because this is a database that everybody needs to have one way or another.
Well, I mean, I'm not really sure I understand what you're saying here because the entire point of this is that you're able to throw out data. So here the idea is you stick some data here and then you need to pay for it to be stored. Yeah. So that you pay for I will store for a month and then after a month you stop paying, you will leave it. Well, then that's a rent system. It is a rent system. Yeah. A rent system. Now you've got Soviet economics because you've got no seriously. This is the thing that people don't see. I agree because they're like the developers are going to set the rent. That's why you have sharding. Because you pretty much grow your storage with the demand. Sure, but I mean, even with sharding, the problem isn't how many shards you have. Sharding is a solution. I mean, I think the sharding big question with sharding is if the shards have different economics. So then you've got coordination costs and pricing costs. Yes. Right. That's what you need to mitigate. Right, but I'm not shitting on sharding. What I'm saying is, one of the things to notice about this is the only way you make it work is it becomes like Filecoin, where you have one fee that's all paid for use of the blockchain now, and then you have another fee that is extracted for going forward. For here's a month of rent or here's 2 months of rent. One of the problems is, okay, well, how do you set that? How does the network even set that? And how does the network set that in a way which is secure and actually market driven? This actually does it. So one way to think about this is that it's a way of actually determining the market price. Because like Ethereum's like, oh, we're going to have rent.
Yeah.
Well, how are they deciding that?
Yeah, they said 10 to 97.
Yeah, they're like, oh, a
per
developer
byte per
picks it.
block. Like literally in the paper it says like 10 to 97.
I referred to that as a fiat. I said it by fiat.
So the way I was deciding the price was actually in dollars based on the price of the hardware.
Let's just use this. It's a market solution.
Well, then describe it to me again.
There are two things. You've got two options. One, you can fix the block size. If you fix the block size, you're forcing a market price to emerge in the context of how big your blocks are. Because this is the key thing here. We're forcing old transactions and new transactions to compete. So the real economic question is you still need to hardcode something, but what you do is you hardcode the fee differential.
So the part I did not understand actually is where is this fee so let's say there's a transaction A with at that moment it had 100 Saito of fee.
Yeah.
Right. So then it will be rebroadcasted later.
Well, what you get is, what gets rebroadcast is there's a new... you get the old transaction, right?
Yeah.
I see.
So the old transaction, let's say, is A1.
Yeah.
And it's signed by the people that made the transaction, right?
Yeah.
Yada, yada, yada. You get a new transaction, and we're going to call this CA1. It's signed by the block creator.
Yeah.
So if you pass it through and it includes the original transaction inside it.
Yeah.
That's why we do 2x, because we assume that the transaction is at max going to be twice the size of the original. But people can validate this to validate the original transaction.
Sure, yeah.
But what you can't do is you're going to validate that this was produced by this has to be valid, it's produced by the block creator, right?
Sure.
So you can't say, the SIGs don't work out unless you have a secondary layer of transaction verification validation. So what you do is you basically take the data and does this work out and sign? Well, no, it fails, but then you say, okay, well, if it fails, then is it the secondary type of rebroadcast transaction?
No, so the part I understand, how am I, if I set here 100, what does that mean? How does that get?
Let's say you have 2 unspent XTO from something
You're also saying it
to...
I know, I'm constantly saying you.
I don't know, we're in Beijing, I mean, if people move on. You can't do it with multiple 2s. Basically, every unspent UTXO, I mean, maybe you can. You might think of a way. Our implementation, every unspent UTXO becomes a new transaction. And if the unspent UTXO if you got 2 unspent UTXO with 100, this is now 98, say. This is now 98. And when you're producing the block, you now have 4 additional units which are included in the fee for the block.
I see. So you just take out the fee out of the mining UTXO?
Right, and if they don't have the fee to pay, if this UTXO only has 0.59, and this works out to 2.67, well, this is dust which falls off the chain. And what you do then is you collect it and you can distribute it to the new block producers in the form of the mining reward. So what you basically get is you get a tax on spare change that no one can use because it's lower than the fee. So the stuff that's useless is all of a sudden useful again. But you also have a way to maintain data on the blockchain at market prices, and this is something Ethereum and them haven't figured out. They don't even know the problems because most people don't, because the only sensible solution is when you have storage and when you have blockchain propagation, people are moving towards 2 payments.
Yeah.
And the problem with the 2 payments approach is, well, okay, we need to pay for bandwidth too. So what are we going to do? The only market solution for that is 3 payments.
Sure.
What if I need to broadcast this data, but I want it to go on an archive node, and then that archiving node, it's a website. Well, I now need to be paying not only for storage but bandwidth, and what happens is it kind of multiplicatively, with every service you expect the blockchain to add, you have to have these different payments. There are Soviet pricing attacks that emerge at scale if these prices are off at the market. With Saito, you don't have that. You don't have that because basically all of this stuff reconciles into the end user and their access to that first node in the network. Because it's that first node in the network, which we know it has all of the data. It has to have all of the data. And it decides to give it to them at what cost. And it decides to give it to them at the cost of what are the fees that you're paying me. So one of the things that Saito does, because we're using market mechanisms, is we're taking these 2, 3, 4 payments, which are arbitrarily decided by developers, and we shrink them into one payment, which is set by market prices.
But the problem is you have no predictability, right? You now don't know when your data will fall off because the market price will change over time.
That's right.
But like it will change when you rebroadcast, not like it. Like it's not.
That's not the problem of the network. That's the problem of the people using the network, though.
Yeah.
Like, we never said, oh, look, there's a problem. The problem is you can't pay me $2 a day.
Yeah, but we're building it for people, right? We're not building the network for network.
No, we're building the network to exist. It's kind of like you're saying, look, the problem with capitalism is you can't guarantee that the price of milk will be 10 cents a liter for 100 years.
Sure.
And it's like, well, yeah, of course I can't guarantee.
Well, I mean, that's a big difference between like you can't guarantee the price of milk tomorrow, and like they have to tomorrow the some price
But we're
versus like 100 years.
we're not talking about it. You could have a transient chain that's 50 years. You could have a transient chain that's 1 year. You could have a transient chain that's 100 years. Bitcoin needs to move towards a transient chain of 50 to 100 years. A human lifetime. If you spend your Bitcoin once in your lifetime, you pay the small fee. If you stick around,
you have an ancestry.
Yeah.
What's it called?
The state tax.
Yeah, the state tax.
Right.
Yeah.
You'd have that anyway because you have to send it to your sons.
Yeah, you need to send it to the children.
Right. But like, what's the trade-off? The trade-off is that the longer the genesis period gets, one, the higher the fee everyone needs to pay, because as it gets longer, the costs of keeping the data for 50 years are on. What you guarantee is it's a market system that won't break.
It's also, think about it the other way around. If storage is coming online super quick, right, and getting a lot cheaper, then actually I get the benefit of that in what I've paid to keep something on chain, right? If storage halves in cost, then the chain can just start accepting more data at the same overall fee value because it's costing less to run, and competitors will come in, right? So the point is it's robust because people aren't going to go out of business or fleece you.
And otherwise, you need to keep changing your pricing mechanism when technical costs emerge.
Yeah.
Because the guy, like, especially in a proof of stake system, because all of a sudden your economic variables are hard coded for cost, and these guys have much more money flowing in because they can efficiently operate at scale, they can attack the
Imagining the politics you're going to get when people are talking about
changing the price.
Yeah, do we accept a pull request to change the price when that pull request was put by Amazon and they're obviously just trying to hurt us all by squeezing us on storage costs.
Yeah. You mean like ProgPow put by NVIDIA?
Yeah. Right. No, but that's the point. If you've got there's two issues to the user determined or the developer determined fee. One is it's set without respect to the market. The other one is it becomes an attack vector because you can actually look at changing that to try and hurt your competitors if you've got a price advantage on the storage.
I like to think this is ideological and linguistic because we present this idea to people and they go, but it's not a permanent blockchain. And it's like, well, why do you believe that BSV is a permanent blockchain? It doesn't have market. It's not permanent. It's going to collapse at some point. And in fact, the irony is that the bigger the blocks get now, any kind of mass market,
the more expensive it is to move.
Like, there's some technological possibilities curve, and maybe if Bitcoin stays below it, it will be able to grow. But even then, there's going to be other networks that come out with lower technical possibility curves, and usage should transition over time.
That to me is the big argument. Is the only case I can see where the permanence makes sense is where you actually get a value from all of the previous data. So, for instance, art provenance or diamond registries or something like that, where there's a real value to me that the entire chain exists.
But that's
and I'm
why
happy to pay for that storage to get it now, and in 100 years it'll be even more valuable.
But that's why I think of it always as just a database, and like whatever you want to record, you record. Everything else is transient.
Well, you can think of it. You can think of this.
Some form of that is
You can think of it as a mechanism for.
I mean, it's just like
you don't even need to rebroadcast because
it's in database.
You can think of this as reindexing. Like the data doesn't even need to be in blocks because the computer knows
But like
know
you
which
can
stuff
think
is
your
there.
transactions are actually in the database, right? And you just like you maintaining the fixed size of this database.
Yeah, it's a bookkeeping mechanism where your money used to be in block 1 and now it's in block 10,001. It doesn't need to be rebroadcast. The point is, when it's spent, all of the systems will say, oh, well, it's the fee in block 1 to 10,001. But yeah, I mean, for us, this isn't even the really special part about Saito, but we look at this and we compare it to like Ethereum's rent, and we're like, look, unless and until people realize they've got the problems are underlying incentive problems, right? Like the fundamental problem is that miners have an economic incentive to take money today, to get paid today, and then, well, we're going to worry about tomorrow.
Well, I mean, rent does solve the problem. I do agree that like fixed price is not market price.
Rent doesn't solve that problem. Because if blocks are huge, I still have an incentive to put as much data on the blockchain today, even if it breaks.
Again, I don't look at like blocks for me is just this transient, like it's like a packet you send it over to CPAP, right? It's not really information you're gonna store.
But here's we're not thinking about blocks. What we're thinking about is think of it this way.
Yeah.
So the reason it solves the problem that Rent doesn't is that you have the structuring of payment in time.
Mm-hmm.
Now, if the payment happens here, and it happens only when the stuff goes into the database, you have perverse incentives. Because it's kind of like BTC. Well, we're going to make the blocks really small and we're going to force a fee market. And that way, because there are high fees, we can pay for forever. You're not paying for forever. You're just giving the people the network today.
That's what storage is then perpetually, like, you know.
Yeah, no, but that's not what this is. What this is...
I mean, I understand. I'm just saying, like, storage rent does solve the problem you're describing. It has a side effect that this is like, storage rent will be like...
It solves the problem here. It doesn't solve the problem where it's actually caused. It's a data management solution, not a solution to incentives. And because it doesn't solve the incentives...
Well, why not? I mean, like, as a validator, you will be you have pretty much a stream of income going forward that you want to hold on to.
It's a solution on the technical level, and it's a better one than... So what I'm saying is, what is the actual incentive problem?
Mm-hmm.
If we can fix this problem, we fix the scaling issue. The incentive problem is miners have incentive to put data on the chain because they get paid today for it immediately. It's a tragedy of the commons problem, right?
They get paid for changing the database, but then it's also paid for maintaining this database.
Sure, but that can fall out of disconnect. It can fall in disconnect when there aren't market prices. So it makes it better because it's leagues better than what's out there.
Well, wait, but let's imagine there is a market price for storage rent.
What I'm saying is, you don't need to have this arbitrary technical solution if you can fix the incentive solution. And the question is, what does the incentive problem even look like? Mm-hmm. Fixing the incentive problem means miners will not put data on the chain unless it's paying enough to do everything that it needs. And that's what this does. Because, no, the payment happens. Why do you get paid? You get paid to get paid for block 10,001. You need to have done all of the work already. So the payment doesn't come first and then the work happens. The work happens and then the payment comes. So the situation traditionally in blockchain, you need to solve it this way because you need to basically be regulating technically the size of the stack. You solve it at the incentive layer because the person who's producing this block doesn't collect enough money to cover their entire cost of operation, but they will go bankrupt.
But like, if I'm for example, a block producer for 10,001, but I haven't done anything for any of these blocks.
Then how do you know what transactions need to be rebroadcast?
What do you mean? I downloaded from somebody's state.
And you verified them? Then you've done the work. That's the work that's needed.
But I haven't maintained this for this period of time. Let's say it's 50 years. Like I haven't spent 50 years of 100 gigabytes or whatever. Terabytes of data, right? This is the expense.
That's
not me like validating is waste. Like this database is such small database validating.
It's almost as if you're talking about the payment for routing and data, which is something else.
Well, no, I'm talking about payment for storage. For this is 50 years of storing 100 gigabytes. This is like versus downloading it once and validating.
The market price changes over time. These guys, I mean, the person.
No, but I mean, like, my incentive here, like, I don't have an incentive for storing it. I should just, like, I will download this data at the moment when I need to do this, and I'll get all the
your
rewards.
incentive to enter the network at any point in time is driven by the profitability of producing blocks now. So the historical cost of producing blocks is paid for out of historical block production. So you can't say, oh, but I haven't done this work for 50 years, because you're not being paid for the past 50 years, you're being paid for this block.
Yeah, but you'll get paid from these transactions that you pretty much, like, rebroadcasted, right?
Yeah.
That you did not maintain for, like...
Well, these guys got paid for the first fee of the 50 years.
Well, they did not, right? That was the first guy.
No. You get the new transaction fee, and then you have the rebroadcasting fee.
But like for this specific transaction, right, that's sitting here, that's been sitting on all of this guy's disks, right? They've only paid for this to the guy who produced block one.
You've got to the fee to include things as a new transaction is the fee for this period. The fee for this period is pushed into market equilibrium by the desire to store data on the chain, which is where this comes from. So, I mean, you're right if you're saying people can come in and people can leave, but you're leaving after 10,000 blocks. You have to do a full genesis period of work before you can produce the next one. Now you can leave. And new people might look and they might say it's really profitable to produce blocks. The nice thing about Saito is they could also say, well, I could produce blocks, or I could route transactions. I'm gonna put stuff in transaction routing. You get the new fee here, and you get the rebroadcasting fee. Technically, they're collected in the same block.
Wait, so just for me to understand, let's say we have like a very simple example. We have one guy who, for 10,000 blocks, been producing blocks, and then really we just only had one transaction in the whole system. You know. It's a set chain.
Okay.
And then somebody showed up. So this guy received, whatever, two Seder right out of like including this transaction. And then spend, X amount of resources to maintain, to keep this, right? Then some guy show up and I download this from him, revalidate, and produce 1,001 blocks.
So how much did he pay to download the blockchain?
Well, that's
what
I'm asking.
Well, I would charge him X plus profit. And if this guy doesn't want to charge him X plus profit, that's okay. Then he's economically rational, and if he falls off the network, that's fine.
So what is it, how do you charge that?
Well, no, that's a private negotiation off chain. You want data from me. We're talking about a massive blockchain moving tons of data. I'm not going to give it to you all for free. The best way you can get it, actually, is if you start feeding me transactions. If you start feeding me things that are worth money to me, of course I'm going to pay you back with data.
But how does it look like from a code perspective?
It doesn't. It's not a code issue.
But spin up a node. How does the node become up to date on the network?
Okay, so BSV is moving. Let's say we've got terabyte blocks.
Okay. No, I'm not talking about just in your network. I spin up a node. How does node become up to date with the network?
Well, you connect to a node and it gives you the data.
Yeah. So you pay for that?
You've got to find someone to give you the data. The nice thing about Saito is, how do I convince you to give me the data? I start giving you money. Now, I can do that two ways. I can pay you explicitly, or I can start feeding you transactions. So for nodes in the routing network, this is why the routing paper
so
is so
I cannot become validator until for a while I ran and pretty much did transition to related transactions.
Look at it the other way. If your expectation is that a blockchain is going to give you exabytes of data for free, you may as well be unwriter and say I'm going to build a Mongo database. All of the data is going to be in there, and we're just going to give users it for free. Of course the economics don't work. The economics don't work at scale because of their costs. The difference is that other blockchains, they assume that the market is going to sort out all of this stuff.
Should we do, or we just record this?
Well, we've been recording so far.
Okay.
So this is good. I'm sure we can. Aside from when I'm talking, do you need a belt?
It's one of the reasons you want to be paying for routing, right? Because as long as you're paying for routing, as the routing nodes start bringing more transactions into the network, well, the people that are moving exabytes of data as core network nodes, you do have market competition between them because they've got the blocks, they've got the data, they want the transactions from routing nodes because that's how they make money.
Yeah.
So what you've got is you've got data as payment. What I think you're asking is you're saying, well, look, tell me exactly how it works. And the answer to that is, if you want an exabyte of data, it's going to cost you. There are two ways of doing it. You negotiate a separate payment, which is a market that forms at the edge of the network. And the network does not specify the terms of that economics. And one of the reasons that like BSV and these other networks are going to have severe economic problems, or like rent and stuff, like if you're letting your economic conditions be determined by code that's in the system, like if the reality differs from that, you either have pricing attack vectors or you have free riding. Saito, we don't actually care your terms of access to the network. We say as long as the network is supporting itself and the network is paying for the transactions that are coming in, you're going to have a guaranteed point of entry because the network always has an incentive to give you a point of entry. Like if you want to say, okay, there's one node, well, that's kind of like Bitcoin. If Bitcoin had one server, why would they share their blocks with you? The difference is in this system, in order to produce blocks, I need the stuff that you've got. And in order for you to get the stuff you've got, I need blocks. There's actually an economic incentive that is going to keep the network open.
No, but why? So let's say you're feeding me transactions. Why would I give you blocks? Previous blocks.
Why would you give me blocks if I'm feeding you transactions? Well, if I
don't want you to produce block. Let's say there's one node, right?
User, router, node.
Yeah. So here's one node. The first node in the system, run by Saito probably. I show up. Yeah.
Okay. I mean,
honestly, and then feeding your transactions.
If we're going to do a one node example, we're going to do a Bitcoin example because Saito already has way more nodes than that.
Well, I mean, okay, sure. So I show up. I feed you transactions.
Yeah. In Bitcoin. Why would a Bitcoin computer give a user a copy of the blockchain?
I mean, we're not talking about Bitcoin.
We're talking about Bitcoin in this example because it's a cognitive thing where people are like, oh, Saito is different. Let's look at this. The problem's not Saito. The question you're asking is blockchain.
You have a bunch of nodes. They all,
they're still Bitcoin nodes. Why would a Bitcoin? Because we're talking about blockchain. We're not talking about Saito. Why would a Bitcoin node give data to a user?
I mean, again, I'm not.
No, it's not.
We don't need to argue about it. There's no reason to give Bitcoin nodes will give it because they're nice. That's the only reason. Because,
that's not why it's going to happen.
No, the reason they give it because they want users to actually be able to transact, and without any data, they cannot.
The payment for the fee is the data. It's the same in Bitcoin. Why are you going to service?
Not really. You can actually not give it. That's my point. You can actually accept transaction and not give data.
Yes. When the network is tiny and storage and bandwidth is free, no one cares. When the network is operating at exabytes a day, the core network, think level 3. Think of actual. This is network peering agreements, right? There is an exchange of value when things cost money. People say, oh, well, Bitcoin works this way. It's like, well, okay, Bitcoin in 2009, I could run it on a Raspberry Pi. This is not a model for scalability. So the answer to your question is that at every point in the network, there's a fee for data trade-off. So if you want someone to give you a copy of the blockchain, you've got two options. You can pay them for it. In a Saito network, you can also pay them for it by starting to scale data because you can be a smaller routing node.
Yeah. So that's the part I don't understand is, let's say you do give them you feed them transactions, right?
Well,
as a relayer node.
Yes.
Right?
Yeah.
Users send you transactions and you send them, and you actually still don't have a blockchain right now. You just started a node.
No, the blockchain exists. So
I'm talking always from perspective of one specific node. Because I'm one person. I'm here. There's maybe other nodes. They have blockchain. I don't have a blockchain. Right? I just started.
Okay.
Yeah. So I'm now receiving transactions. I'm So signing them and then sending them to the nodes I think have blockchain. First of all, I don't know they have blockchain.
Think of Bitcoin. You got a permanent ledger that's, let's say, 10 exabytes. You need the entire ledger to validate. Theoretically, I mean, people are moving towards systems where you don't need to download the blockchain, which is basically saying that it's not a permanent ledger and it's just,
it's a database with a transaction log.
So it's basically a temporary ledger where you actually have no guarantees of data being on the blockchain, which is actually why Saito matters, because it provides guarantees in an economic system where other blockchains can't. Why would a Bitcoin node send you 10 exabytes of data so you can do the work required? They probably would, but they're probably going to ask you to pay for it. If you talk to BSV people, all of the rage on Twitter is about like archive nodes. The idea is that, oh, well, we accept that the nodes in the network will do this. There's a separate node that will pay for it. The problem is, again, it's like, well, okay, but coordination costs, and why if I'm using a blockchain because I don't want to pay coordination costs? It's one network. So all of a sudden, I have to deal with archiving nodes. I've now got 2 payments. Not only do I have 2 payments, use of the network, use of the archive node, all of my users now have 2 payments. So we've now got 4 payments instead of 1 payment, and we've got coordination costs of which archiving nodes we've been paying for. Part of the value of this system is that this is a ridiculous system. The only reason people think that this is sensible is because they haven't solved the problem at the underlying incentive layer. And going back to what you said, this is a viable solution. And I'm not trying to criticize this because this is leaps better. And what I'm trying to point out is that if you have a system that solves things at the incentive layer, you don't need this because things like rent start self-regulating automatically.
So, I mean, like before we get into this, like I'm just trying to understand how would it work, right? So like I'm one node. I like boot up it on my computer. Right. So at this point, first of all, I need to find peers.
You got to find a peer.
So let's say I know about some of them. I connect to them. And this point, right? Like if I want to be block producer at some point, right? I need to negotiate with them to give me the current blockchain.
Well, you need to do that in any blockchain.
I'm not talking about any blockchain. Talking about Saito.
Let's say.
You don't need to convince me that Bitcoin has issues.
Okay.
that's not the point.
Here's what I said.
I'm just trying to understand how it will work.
The size of the chain determines.
The first question I have is, I connected to a node. How do I know? Like I'm gonna pay them. How do I know they have actual blockchain?
Let's say the cost is $10,000 per. Actually, let's say it's $10 per block or something. Even at massive scales, like $10,000 per block.
You mean to $10 per
Existing
sending a block or
bandwidth or something? Okay. So like a 10,000 block chain is like $100,000 or something, right? So you've got 2 options. And it's the same with Bitcoin. This is not a Saito thing. This is it's the economics of blockchain, right? You've got 2 options. Let's start with Bitcoin because where we get better than Bitcoin, we'll explain. You pay this guy $10 and he gives you the data.
What if it's fake data?
Well, what if it's fake data in Bitcoin?
I mean, that's why I don't pay in Bitcoin. Well, they just give me data and then validate it's correct data.
Yeah, great. If you can have a blockchain where everything is free, it's
no, but like I'm asking how do you pay in a way that like only pays if it's a valid data?
How do you do that in Bitcoin?
You don't. That's why there is no such.
So your solution. We're saying there's an economic problem because you need to pay for the network.
I'm saying there is a problem. I'm saying tell me the solution that actually provides. Like
that's not the problem Saito solves.
Okay.
Saito doesn't solve you for someone sets up a sign and says, hey, I'm a Bitcoin node. I can send you the blockchain. It's going to cost $50,000 because it's huge. You go up to that archiving node, you pay the money, and they send you fake data. That's not a solved problem. That's not a solved problem in any blockchain because if you want,
there is some solutions for this.
Well, I mean, there's smart ways to do it. Like you find out what the actual hash is at the tail of the chain, and you sync the chain backwards. That's one solution. You still need to actually yourself figure out what the last hash is.
Yeah. So how do you do that?
Well, you can do that in Bitcoin. This isn't the problem that we're worried about.
Okay.
The problem that we're worried about. Let's move on. You're saying let's assume that they're going to give you good data.
Okay.
And honestly, assuming they're going to give you bad data is not. It's not a real world problem at this point. It's not even a real world problem.
Spin up nodes and get money for free.
Well, you've got 2 choices, right? You gotta pay him $10.
Yeah.
The Bitcoin solution is I pay you $10 and maybe I collect this money from users that I serve the data to. And so with all of these users, I have this off-chain private economy, right? So I'm going to collect on PayPal, I'm going to collect $3, and this guy's a nice guy and he pays me $5, or maybe he's an idiot. And so my profit's $1, and hey, I'm in the business of dealing with this. This is the traditional internet peering arrangement. At every point in the network, you have people making off-internet exchanges of value and payments. So this is maybe me and my ISP. I pay my ISP $30 a month. This guy's paying $50 a month. The ISP is mediating the economic agreements with all of us and with the chain.
Sure.
Okay? Saito replaces this because what you've got is you've got the data itself that's sent that has value. So if I'm a user and I'm sending transactions onto the network, this node gets paid for redirecting the data.
Yeah.
And so you've got the transactions that have fees, and so the fee is paid for by use of the data, and the data comes back through. What this guy has to do is he basically collects the money, sends it into the network, and he gets paid for that. So economically, what you've got is you've got a replacement of kind of commercial ISPs that have these private arrangements with people with essentially a uniform cost of internet access, where market forces basically make people flexible.
So I understand this part. The problem that I have with this is that when this node, let's say this is new ISP, right?
Yeah.
I'm starting my new ISP. I need to connect with some folks.
Yeah.
Right? And we'll be sending them transactions, and let's say you have
Your problem's with Bitcoin. You're like, your problem is, you're like, of course, if you want to serve someone on the blockchain, you've got to serve on the blockchain. This is a Bitcoin problem. This is the Bitcoin network.
Sure.
The Bitcoin network is moving exabytes of data.
Yeah.
And you're like, okay, yeah, but I want them to send me exabytes of data. The difference is actually with Saito, one of the ways this improves is this guy, at small scale, he does not need exabytes of data.
Sure.
Because maybe he's giving these guys light blocks. So maybe he only needs a third of the blockchain. So because he only needs a third of the blockchain, he can actually pay to get cryptographically verifiable a third of the blockchain. That's good enough for the users because they can verify that the data is solid, which means that the cost here is not the same as getting a full exabyte of data. And what you've actually got by subsidizing routing is an economic structure where, in addition for paying for block production, you're also paying for light block production. So, and that's CPU intensive. So you actually, servicing users, there's a reason for these nodes to exist independently of these nodes. Because these guys, they're moving masses of data and they're focused on that. They're focused on, it's like, level 3. Level 3 does not want to give you individual access to the internet because that's not their business model. But these guys, there's space in the system for them because what they can do is they can focus on, okay, well, you're a light client, but you're not really a heavy client. You don't make heavy demands. So I'll accept transactions from you that pay this fee as long as it's X per month. And the whole thing becomes systematized in the economics of the blockchain. So, basically everything that is sort of arbitrary about the Bitcoin system in terms of these ancillary nodes becomes streamlined in the economics of the blockchain itself. So you can kind of think of it as like an internet peering system where instead of people having to arbitrarily decide what their data flows cost, the fact that it is a data flow means that it has money. And that reconciles the economic issue. It also, the guarantee it provides of net neutrality is that you've got to realize that the transactions that are profitable to this guy are just as profitable, if not more profitable, to this guy. So this guy, he can switch over here if he doesn't get good terms. And we actually do drive down to utility pricing for this sort of revenue thing. This can't happen in Bitcoin. In Bitcoin, well, this guy's got to get the full block, or he's got to negotiate stuff off chain.
But like here, you also need to. This is like, let's say you only know about this node right now. Like for you to actually find out about all those nodes, either this guy needs to tell you about it, or you need to find it somehow off chain.
Well, look, if we're being honest, the Bitcoin software, the pure finding software is insecure.
Yeah.
So like. There's no reason that any blockchain's pure finding software is less secure than others. It's not a viable criticism. It's kind of like saying, yes, but gravity is hurting your plane. It's like gravity is hurting every plane. When someone figures out a solution to gravity, like, any blockchain can do that.
Well, my problem, like why am I pointing all those problems is that, like in Bitcoin right now, there is no payment for this.
Well, yes, I know, and that's why Bitcoin collapses.
But that's why there's like, yes, it's insecure, yes, there's all these problems.
Well, no.
Because there's no payment, there's no like economic incentive to try to trade.
No. Here's my disagreement. You're saying, well, look at this problem. We're talking about Bitcoin.
Yeah.
So you're saying, look, the problem is you guys in your system, you actually pay the network to survive, and it's like, yes, but that's the entire point of a blockchain.
But like as soon as you in Seder, right, you're adding money to this communication.
No. There's no separate payment in Saito. You're just the payment comes out of the fees. There's no new payment. Where does the money that is here comes from? This is the money that used to go to miners.
Okay, so okay.
Like the Bitcoin network, you've got to have all of these separate negotiations because all of the money is going to the guy in like Xinjiang who's got the server farm.
Okay,
this is saying the money that used to go to the miners is now paying for the network. The network is the ASIC. Mm-hmm. The way you make money in Saito is you have to be really efficient at positioning your servers, finding users, and giving them a good deal on the data.
I think the thing to understand is if you're thinking about scale, genuine scale, imagine that each of those core nodes, right? It's a silly situation. Imagine it only has one switch, right? So you're literally deciding who gets the 16 ports outbound, right? And you've actually got to pick the best people to be most profitable, right? Because we're talking about a scaling network. If people can randomly connect to a network like that, whether or not they provide useful incoming traffic, you can simply attack the network by just sequentially adding Raspberry Pis, setting the chain, and then formatting them and doing it again.
Well, I mean that's what I'm trying to figure out how all this works.
Well, I
think the thing there is you will need to negotiate connections to the core network.
But the negotiation happens off chain.
Look,
right.
Here's the example.
These pipes, these nodes here, these routes here, will cost in the order of thousands of dollars a day to run. So you're not going to give them away.
Think of it this way. Fundamentally, the first point is, and it's one thing many people coming to Saito have, the misconceptions not about Saito, it's about blockchain. Like they think, well, Bitcoin does this for free, therefore Bitcoin will do this for free at 10 exabytes a day. And it's like, no, Bitcoin does this for free because I get a certain quota, right? Think about this though. This US server has its own economics. Now imagine that China bans Bitcoin, China bans Saito, whatever. Now, you get a lot of really fat users in China that are willing to pay a really high fee to get their money in or out of the country. Okay, that's a really high fee. These transactions are worth a lot of money. Now, you can get a node starting up in Hong Kong.
Yeah.
And when I say a node, this can literally be a guy walking across the border with a number memorized in his head. And the transactions that he's routing to the system are very few.
Yeah.
But they're really fat transactions. Because of that, this guy is able to pass them to this node. And he'll get the exact same amount of data that this guy's getting. And he might send a guy walking back across the border.
Just so I understand, when you say data, what do you mean by that?
Blockchain data.
Like the blocks,
Well, users connect to the blockchain. They get services from the blockchain. Abstract the blockchain. Users pay fees, and in return, the nodes in the network give them.
What is the form of this data?
Well, what data does the Bitcoin network give?
Like, there's blocks that users don't care.
Some users might.
There's transactions that users don't care except their own, and there's UTXOs.
There's proofs. Users do care about transactions that aren't their own because you're going to have applications that are operating. So you might say, like, if we're both using a Facebook application on Saito, I might say, well, we're friends, so I want the Facebook applications that you send. So,
Facebook transactions.
Yeah, like you might send a transaction, and inside one of the reasons we want big data in a blockchain is like in Saito, when you make a transaction, you've got essentially a JSON object where you say like name Facebook, you know, and you can put the post there right in the transaction because we support the economics of scale. You could also say, oh, my post is on this server. Or maybe you've got a name card circulating around the blockchain that says, this is where to go for it, and this is post ID 86704. Whatever it is, like there are lots of ways in which people want data. Other blockchains are compartmentalizing this and splitting this because they don't actually have a viable means for handling this. But, you know, it's like
what do you mean by proof?
like, I don't know, an SBV proof, a cryptographic proof.
Of transaction or for UTXO?
Well, you know, like a Merkle tree proof, where I'm not only proving to you that this is your transaction, I'm providing other sources, right? Like,
yeah, I mean, like, but when I think transactions as data, you do need to include proofs that this is part of the blockchain, otherwise.
well, yeah, I mean, if you send the full, yeah, exactly.
Yeah, okay.
But I mean, you know, like this sort of thing, when you're dealing with clients that aren't getting the full data, yeah, there's a data need there.
Yeah, and I'm just like trying to, because like what I think of data from blockchain is is different.
Yeah.
That's all.
I mean,
Again, just because the way I look at blockchain is a database.
yeah,
Like literal, let's just say key value database
Yeah.
that is shared between everybody and has a very specific rules of state transition. That's how I think of blockchain. You think of blockchain very differently.
well, we're the applications you're going to use something like Saito on are generally broadcast applications, right? Like, so, you know, if you want the stuff to stick in the debate, what it's really doing the first time around is it's just ordering the transactions.
Yeah.
If you start looping it, well, then that's a database application. But if you're going to use it as a database application, you're probably going to want to tweak the rebroadcasted feed. The point is that this stuff, like, this isn't Saito at all. This is just blockchain. The problem is, like, the reason we need to talk about it is because people don't think about this stuff at all. They're like, well, I use Bitcoin. I connect to the peer-to-peer network. And, like, the fundamental definition of a blockchain for us is like, what's special about Bitcoin when it came out? There were databases before. There were consensus systems before. What was special is it was the first network that supported itself financially.
Mm-hmm.
So it's a network that exists without an owner, where there are financial incentives to join. That, to us, is what is the fundamental definition of a blockchain. And, you know, other people don't, they're like, oh, well, Bitcoin, well, you're going to connect to the peer-to-peer network. Well, it's like, well, no, because then you have free riding problems. And at scale, the peer-to-peer network is not going to operate exabyte nodes. So all of these issues with, like, who pays for what and who pays for what, it's sort of like the Bitcoin or the old blockchain mindset, because the old blockchain mindset at scale, the only way you can convince someone to do something is having a separate economic agreement off-chain that needs to be mediated. The advantage of the Saito system is all of that stuff just moves on-chain. So I can pay you off-chain for this stuff. But if I'm paying a fee for the network, that fee is enough to incentivize everything to organize itself. And so it's like the fee that's paid for in mining is now paying for the network.
But let's say, so I'm this guy.
Yep.
Right, I brought in a few transactions. I sent them to this node.
Yeah. You're probably also going to send them to this guy too.
Sure. I send it to a few guys. And then why they care at all giving me back data?
Well, if a transaction originates here and it goes through here,
Yeah.
and it goes here and here,
Yeah.
Whoever has the transaction and puts that into a block,
Yeah.
they're statistically going to get paid.
Sure. They got paid. They're good.
Yeah, they're going to get paid, and they're going to get paid.
Sure.
If this guy produces a block, this guy's not going to get paid.
Yeah. So this guy's get paid.
Yeah.
Why is this guy sending data to
He wants
HK node?
Well, because he wants to get the transactions.
But he already got transactions.
If I connect to my ISP and my ISP sends data to Facebook, why does my through Comcast?
Mm-hmm.
Why does my ISP send me the Facebook data back?
Well, I mean, here, like, you already paid for it, right? It's as if like you paid $30 for signing up, but then they didn't give you any data.
These aren't Saito questions. This is a data network Bitcoin question, right? Like, I can send a Bitcoin transaction to you, but why are you going to send me Bitcoin data back?
Well, I mean, from my perspective, you're trying to solve incentive problems.
Yes.
And like saying that this is a Bitcoin problem is not really helping. Because
No. This is the solution here. The solution is the user P, the blockchain nodes give you data.
Mm-hmm.
The users pay fees.
Yeah.
Now, the problem with Bitcoin is that actually it's this. It's users pay miners.
Yeah.
Blockchain gives data.
Well,
That's your problem with
miners
traditional
give data
blockchains.
in reality.
Well, then why does everyone say, oh, well, you know, we say we go talk to people and we point out that transaction propagation is not incentivized.
Yeah.
And they say, well, that's okay, you'll get that from the peer-to-peer network, which is operating for free.
Well, I mean, what should, like in Bitcoin, let's say, what should be miners give data. You send it to miners, miners give data.
Yes, this should be Bitcoin, but this is not Bitcoin. Miners do not service the peer-to-peer network. If miners, there's so many cases where it's self-evident. If miners serve, like Craig Wright wrote a blog post where he's like, the great mining swindle, where he's talking about, he's like, it's an economic system. The first thing miners have to do is invest in network infrastructure.
Yeah.
So empirically, Craig Wright is saying this is not Bitcoin because he's saying actually they don't understand the economics of Bitcoin, they're investing in the wrong thing. Mm-hmm. Well, first of all, if you're creating a market system and people are not doing what you want them to do, the first thing you have to say is like, well, what are we incentivizing? What we're incentivizing is this: the fee goes towards miners, and then somebody has to do stuff for free.
Yeah.
And this is like 99% of most people who are working on scaling tech, they're working on ways to push costs around. Like, oh, let's get IPFS. Like, we have a network that's printing money, fees. Mm-hmm. We can't pay for storage ourselves, so we're going to put petabytes on IPFS. Like, that's just it's pushing the problem somewhere else. You get like Blockstack, where they're like, well, we can't solve this problem.
But okay, so now the question that I'm asked is exactly about this, right? Like what I'm hearing right now, which I'm trying to figure out why I'm wrong, is you say fees go to block producers.
Well, fees go to the network, and the network gives you data. Yeah.
Block producers who produce blocks.
Technically, the fees...
And to relayers, the people who relay.
Yes.
And then data, so far I did not understand why data would come from these guys.
Well, block producers get the data.
So fee goes to relayers, and relayers send it to block producers.
Okay. This is going to be really simple. I'm going to leave this up because this is good. This is your structure of the network. You have users.
Yeah.
They don't connect to the block producers.
Yeah.
They're connecting to the relay.
Sure.
The relay, let's say, is going to connect to block producers.
Yeah.
That's simplified because the relay could connect to another relay. Right? The data goes back in this direction.
My point here is that I can draw this arrow as well.
Well, no. You can't draw this arrow because empirically it doesn't happen.
Well,
if empirically that happened, the Bitcoin
I think the question is,
happen.
what empirical evidence is that this would happen?
Well, it's not the empirical evidence.
No, you got.
It's an incentive. It's incentive question.
This is. Let's make this clearer because I don't know. I don't know how it's.
Just to be explicit here. I'm not saying that there is a solution for this. I'm trying to figure out if you guys have a solution.
This is the traditional system, right?
Sure.
If there's any question that this isn't, well, you can say, well, miners will service the users. That's the Craig Wright argument of miners will pay for Bitcoin, the network, because if they don't get paid. Yeah. And so people are like, oh, well, this is Bitcoin. People think this is Bitcoin. Miners will do this because they don't get paid. The problem is there are free rider pressures. Miners don't want to do it. Miners want to pass the buck.
But let's imagine a world where all of those people who right now giving data, they stop.
That's Bitcoin. These are volunteers.
Yeah, so let's say they all stop. Right now we do have a lot of volunteers. Let's say they all stop. What's going to happen with Bitcoin?
Whichever miner steps up and starts volunteering is less profitable than all of the other miners.
That's not true because who are you going to send to?
Any miner,
But why would you send it to other miners?
I've got it. So let's do this then. Let's say, assuming the volunteers disappear, what you're really asking is you're saying, what is the economic problem with Bitcoin? Or what is one economic problem with Bitcoin? So let's assume we have a Bitcoin world where we have 3 miners. And these miners, because the peer-to-peer network vanishes, the miners are forced to spend a lot of money to service users.
Yes.
So the users give them fees, and the miners give the users transactions.
Mm-hmm.
And we're going to replicate this elsewhere. So we've got miners and we've got users. This is a fundamental. You go back to Craig Wright and he says, the first job of a miner is to propagate transactions. Mm-hmm. So Craig Wright sees like a small network where the miners all connect with the other miners. We can have big blocks. The miners are going to pay for this high throughput bandwidth because, of course, they all want to connect to each other.
Yeah.
So maybe there's 10, maybe there's 100. Who knows how many miners there are? Note, we got the fee and we've got the data.
Yeah.
Now, the economic incentives are not, very strictly, miners are not incentivized to share that transaction. Because if miners share that transaction, these two guys can free ride on him.
Yes. So they just accumulate their own and then propagate the block.
Right. Well, what you happen then is you actually, and it's one of the reasons you need to solve this.
Yeah.
What you've done is you've killed the openness of the network. Because now all of a sudden, if I'm a small miner, if I'm a small miner, no one's going to send me stuff because I'm not producing enough blocks to actually get fast confirmations. So the economic problems in Bitcoin are solvable, but they're solvable if you kill the openness of the network and if you have collusion between the nodes of the network. Because what happens when you get these free rider pressures is that these miners, they need to collude with each other to make sure that no one is free riding.
Yeah.
And that only...
I can simplify it saying the block is the way to propagate transactions. Because that's a package thing that says, here I sign on it, and this is what you can propagate.
Yes.
And then when you do that, then
Yes.
that's pretty much, it becomes a relayer of a blocks, not a layer of transactions.
Right. The point is you've got a free rider problem, right? Because miners have a choice. They can propagate the transactions.
So we never propagate transactions. We always propagate just blocks.
Well, if you don't propagate transactions in your Bitcoin, and let's say what am I going to do as a user? I'm going to
send it to one guy. If you didn't include it, you send it to another guy.
I'm going to send it to the biggest guy in the bunch.
Yeah.
And what that means is the market share of the guys that are big, they get even bigger.
Yeah.
And the market share of the guys that are small, they go out of business. So you've got this economic situation where the network just becomes PayPal. I mean, maybe it becomes PayPal with 3 people, but this is not what people want with an open network. So
I am fully with you.
Right. So go back to this system. This is the system you're describing. You said, well, look, if the P2P miners don't give data, okay, well, then the miners have to, but the cost is that your blockchain is destroyed.
Yes.
What Saito does is say, because of this, because the relays are being paid, we don't need volunteers in the system, but we don't get that.
So
we actually still have an open system under Saito.
So where I'm coming from, and this is now let's imagine this is Saito, right? And this is instead of
Saito is a lot better.
Sure. So you have the user, right? Which sends fees.
Yeah. And let's say it's a routing node.
It's a routing node, right? So in reality, routing node should just if it has a bunch of users, you should just package.
Think of a routing node as the peer-to-peer network in Bitcoin.
I understand. I'm just okay. So they send to a block producer, right?
Yes.
Now.
Well, here's the thing to know. There are many things to know, but one of the things to know is if I'm a relay node, as soon as I get the transaction into a block, I'm making money.
Yes.
So I don't care who has it. In fact, I want to send it to multiple block producers because I want competition, including my transaction in a block. If you remember the mechanism where we talked about the burn fee and stuff, if you just give your transactions to one guy, he can hold on to them for a long time, and then his percentage of the fee starts rising. So if I'm a routing node, the way I maximize my own income is making sure that there's no monopolization downstream. That's what we want the peer-to-peer network to do in Bitcoin. The peer-to-peer network is supposed to be sending stuff out to a bunch of miners. Because if it only sends it to one, you actually have these economic problems that people don't talk about. But
just in that model, right? Miner, you have 3 miners, let's say. Why am I not sending it to all of them?
Well, I mean, you could.
Yeah.
How do you even know who the miners are?
Well,
and
what producers are.
Okay, well you can hypothetically say we're going to fix Bitcoin.
I'm not trying to fix Bitcoin. I'm just
no.
When you're saying you're solving incentive problems with Bitcoin, I'm trying to understand exactly which of the things you're solving.
What are the costs to this system? One, you've got coordination costs. The user of the network, these are supposed to be done. In Saito, the user makes a fee, he gives it on. The network takes care of it all. We've now got the user making coordination costs because the user needs to keep track of who's in the network, send their transactions to all of them. That's just ridiculous. 2, the bandwidth costs of the system are massive.
In Bitcoin, right, I can make this where it's a UTXO which pays to this guy.
Yes, you can.
So
That would be like a Bitcoin network where you're making a private payment. Why should users have to? I mean, if you're using the network, you're paying a fee. Why should you pay like 5 different fees as part of making a transaction? Users could do that.
So what I'm trying to understand is like how, like this loses openness, I agree with you, and requires collusion. Like here, my problem is this, is right now, when you propagate these transactions, these block producers, at least as far as I see, don't have an incentive to pretty much inform this relay node or the user about the results.
Why am I going to send money to someone if they're not? Why? It's like.
But like you don't know anybody else. That's the same.
I think that's the point you need to make really clear. This is an ongoing thing.
I really don't understand.
No,
this is my ISP.
I think it's thoroughly. It is
why would Comcast
it's
get my
confusing.
ISP?
It's very confusing the way it's been described so far. This is a flow.
Yeah.
Right. This user is not a one-off person. In the Hong Kong example, that totally confuses the whole case. Because in the Hong Kong example, you're right. Why would I give that guy anything unless I know he's coming back next week? Right? I don't. He's just some guy with a random number, right? The point is that this is a flow, right? This guy's valuable to me.
But if you're saying if it's recurring, that means it's not open. Because open means I will, destroy this, create a new one.
No, I just fundamentally disagree with your character. If I'm this guy,
yeah,
I'm not going to give this guy money if he's using nothing in return. I mean, if your entire idea of your criticism is that I'm going to give money to something, like I'm giving you a lot of money,
well, that's why
you're giving me nothing. No, screw that. I'm not giving that to you. The stuff, my transactions have real value. If you won't, and I need to give this guy data for him to pay me.
Yeah.
If this guy's not going to pay me in data, screw that. If he's not going to pay me in data,
that's the way.
my data's worth money. I've got a lot of choices. There are tons of block producers on the network.
It's more like a trading relationship.
And my fee has value to all of them.
Okay, so my point here is that there needs to be a relationship between the relay node and the block producer.
Well, by definition, there's a relationship.
No, I think it's confusing if you haven't said that.
But when I say relationship, in my head, what this means is like something more than just I connected, done something, and left. Like it's an ongoing relationship, which by definition is kind of a form of collusion.
Well,
you cannot collude if you just came in and paid something and left. If we're talking on an ongoing basis, that's way kind of
so. I'm
just saying, like if the new guy comes in, right? These guys don't know if he's gonna feed the money going forward, right? He maybe just came in, wants to download a lot of data and leave.
I can connect to Bitcoin.com and you've got the same problem. That's not even a problem. Bitcoin, it's like the idea is that these other blockchains, people are going to do all of this work for free, but in Saito, suddenly because we pay for routing, data flows stop flowing backwards. Like that just doesn't make any sense to me. Every other blockchain, users connect to a node, they pay a fee, and the node gives them data, right? And we've already noted that, in fact, there are massive problems with this because it closes collusion and openness. What you want to do is you want to say, but I got a problem with Saito because even though this guy, he wants to be profitable, right? How the hell does he service the user? He services the user. Why is the user using this guy? Because he gets data. Why is this guy using the block producer? Because he gets data. The fee flows in, the data flows out. And I don't understand how you can be like, well, I see this, but I don't see why data. Because that's an incredibly selective, and I mean, honestly, it's kind of dishonest because you're perfectly happy to say, okay, well, assume this.
No, I'm not saying this. This is not happening. We know this is not happening.
Yeah, but this will happen because the reason Bitcoin has problems is because of this, and then the archetype of the network with mining and incentive propagation. The reason the collusion and the incentive problems exist is because there's no incentive to propagate. In Saito, there's an incentive to propagate. One of the fundamental problems that's solved is this guy. Why doesn't he just hoard all of the transactions? And the answer is because he's indifferent to whether he produces a block or whether any of these people do. All he wants is the most efficient path. And so what you're going to get, the economic pressures push towards optimization. Maybe this guy says, look, you're asking for a lot of data, you're not giving me enough money, I'm not going to service you. There is going to be a market price for data. The point is you can pay the market price off-chain, which is what every other blockchain is doing because, like you said, with relays, I've got to have a separate payment for this, or I can have a separate payment for this, or I can go through the effort of doing all of this manually, which is ridiculous. With Saito, The fact that people are indifferent means you just pay your fee and the incentives encourage openness. The big challenge is how do you make this guy indifferent to hoarding things that are worth money? Because that's one of the Bitcoin things. It's like, well, if I'm paying for money, and like Bitcoin people, like BitPay, the people don't generally see the problems because they're used to how it works now. So like look at Ethereum with Infura. Vitalik just wrote this really long piece on collusion. I don't know if you read it, where he's talking about how you can reduce collusion in the system and keep the system honest, right? At the Stanford Blockchain Conference, we were hearing, I don't know what you heard, the biggest number I heard was 90%, but it seems that Infura is processing
at least 80% of
at least 80% of network traffic.
Yeah.
So if Infura, and they're not profitable, so let's say most of that's outgoing, let's say they're collecting 70% of network fees.
Yeah.
How do they make money from having 70% of network fees? The collusion that matters is the collusion between the person that the transactions are worth money. It's the collusion between Infura and the node in the network it gives it to. And for Infura to make money, this node in the network needs to be guaranteed that it will make money too. So what's going to happen is Infura gives the transactions to this node in exchange for the payment, and this guy's not going to propagate. That's also a Bitcoin problem, because look at BitPay, right? Okay, well, BitPay is the source of a lot of transactions. So if users are making transactions through BitPay service, why doesn't BitPay say, well, okay, we're relaying them, we're going to send them to Bitmain? Why will we send them to Bitmain? Like, well, because if we send them to Bitmain, we get paid, and Bitmain gets paid, right? Again, the collusion is lost. With this system, you're guaranteeing openness because the economic incentives are driven in both ways. So yes, there's still a price. The price for data is the money that's made. And the individuals can make their individual judgments about who they connect to and determine, look, am I making money in the system? The difference is Saito actually incentivizes efficiency. If I'm a block producer and I can say, look, I will give you the data for fewer fees, well, that's actually going to make me more profitable because I'm paying less for the data that I need to service the users.
You're just, as a relayer, you specify how much you take out?
Well, if I have $10,000 in fees per block, maybe I give some to a second guy. I send $8,000 to this guy, and I send $2,000 to this guy.
I received this transaction, right? There's a specific fee. Where did 10,000 come from?
10,000 came from trying to explain the fee and the data. The point is that, okay, one way, there are various ways in Saito. We haven't talked about proof of transactions. And because we haven't talked about proof of transactions, it's sort of...
we can start maybe more from the beginning.
One example would be the block producer doesn't wait as long before producing a block. Because what that does is that says, like, maybe with the old one, they're like, look, you're going to send me the transactions, but I'm going to hoard them. Or maybe I don't want, look, this transaction fee is too low for me. Don't bother sending me those transactions. If it's not 0.005 or above, I don't care. Now, you get a cheaper block producer that says 0.01 is fine. All of a sudden, this guy can go to these users and say, look,
my minimum.
I can get you for a fifth of the price. Because the savings actually pass, the efficiency passes through. But yeah, fundamentally, it's a fee for data exchange at every point in the stage. The point is, it's that way with every blockchain. The difference is they don't know how to reconcile. They don't know how to have the same person give the data without turning their network into PayPal. Saito's figured out how to do it because Saito knows how to pay both this person and this person in a way where block producers, the way they make money is more competition among relays. And the way relays make money is more competition among block producers. So there's this, like every node in the network, you want, like the relay is going to send its transaction to two people because that's how you get things efficient.
So faster.
So like the user doesn't need to constantly maintain the state of the network and monitor all of this stuff. And it doesn't need to have a separate payment from the routing node because if it pays the usual fee for the routing node, the routing node is going to make sure it gets propagated quickly. And you can have different things, like the fact that the fee halves with every stop. If you get lovely properties in addition to the optimizing network, because if there's a useless node in here, the way these guys maximize their income is connecting directly, right? Because if you connect directly, you're gonna be at least 20 to 30% more profitable. But
and I think a good way to understand this as well is if you're looking at right at the edge of the network where you're dealing with these guys, right? This will start to look a little bit like, because you're worried about kind of peer discovery and those sorts of like, how do people know?
I can list the words I have, right? One is peer discovery, just because like you have an incentive to, as a relayer at least, to be the only relayer that user knows.
yes.
As a block producer, you have incentive to be only block producer relayer knows. Right?
Same in Bitcoin. The difference is the user. The relayer, you've got a bunch of variables that are different, right?
So in Bitcoin, because of P2P part, actually you have an incentive to kick people out and send them to other people.
Right. Look. Bitcoin's peer-to-peer. The peer-to-peer network is not a fundamental part of the blockchain.
Sure,
it's part of the network management. So if you're saying I'm
not saying. No. Moving on from that.
The economic incentives. You've got the relays.
Yeah.
The relays are crying out for users.
Yes.
Right. It's kind of like you want to use the internet, and there are 25 ISPs that want to give you free internet access because when you visit Facebook, they get paid.
Yeah.
So if our big concern is that a relay wants to monopolize, well, of course it does.
I think a good way to explain how this will work is, right, these guys, like ISPs, will
advertise
and offer packages to these guys, right? Because they're in the business of retail sales, so they might do stuff like say, I will give you I will give you this amount of fees, and I'll give you a bonus, and I'll pay those myself, whatever, to come and join me, right? So they're in as good a competition as we'll get, right? Now, given that, these guys are interested in picking up high-value relayers, right? So they're looking at who's got a great business model, who's getting a lot of users, and has fresh transaction value I'm not seeing elsewhere. Right? So then, yes, this will need to be an ongoing relationship. But these guys might have a simple way of contacting us and saying, I've got transaction value, right? And so I'm some kind of institution, I'm putting one of these in my building, I have this amount of fees, would you like that from me? When you get to these guys, the big block producers in the middle, they're going to negotiate like ISPs do now ISPs now rent space on their cables years in advance, and they hold auctions and stuff, and they make bilateral agreements to say, look, I'll route your excess when you have it, etc. That's going to happen between these guys because they'll need to.
Well, 2 points. One, break the model, because the model that people are thinking about is the Bitcoin model, which is where the cognitive differences come from. Because the cognitive differences really are pretending that this model is the model where the same people that get the money give you the data. That's where the free rider problem comes in. The first point is that this doesn't need to be known on the peer-to-peer network. This can be an application.
Sure.
So like in Saito, one of the things we've got is the arcade, right? So why would you set up an email server? Why would you set up an app server? Well, you set up the application because, maybe you deal with the data over JavaScript. You use the in-browser function. Now you're relay number one. You now have a way to actually make money online that doesn't require advertisements, and it just requires you to build an application people want to use. Because if they use the application, like if they make a tweet, well, the fee, part of it's going to go to you. So there are different models. Like if the users don't care, I want to use the EA system, and the EA system is using a blockchain because it wants to collect my tokens because I'm getting them from an advertising network, right? The advertising network is buying the tokens from the block producers. You've got, if you can create that first hop that's not competitive, you can make a lot of money. On the other hand, if users are really concerned, they're like, well, I actually want cheaper, maybe they connect to 2 or 3. The other really interesting thing is note that in the Saito mechanism, though we didn't go into it, the depth of block propagation depends on the profitability of the fee, essentially the measure of work. So if you pay a really low fee, your fee might go here. And if that's a block producer, that's okay. But it might take 12 hours for them to get enough work to produce a block. If you pay the equivalent of a $5 fee, it routes through the network and it gets divided because this is a high value transaction. So you've got this wonderful property where the higher fee means deeper network penetration. So deeper network that's faster confirmation. Or you could do the work of trying to figure out who to broadcast to. But, you know, a lot of these guys, they're probably going to be, a lot of the nodes are probably not going to be public because they'd be like, if I'm routing exabytes of data, I don't want to deal with individual user connections. I want to deal with people who aggregate them. It's like the internet, you know?
Yeah.
So it's the economic model that takes this and it turns it into users have a one-to-one relationship with network operators. And network operators replace miners, and that's why the network works. Because the data fee exchange becomes unified at every hop in the network. Anyway, it's the economic model. It's not how the consensus mechanism works.
Yeah. No, I mean, I think that's one of the interesting parts as well, right?
Yeah. I mean, you know, like this is possible. The peer-to-peer network is possible too.
Well, what I mean is, like, in theory, what you can do to just take actually ideas you have and you can implement them in Bitcoin by just like creating UTXOs which pay layers.
Well, yeah, but then what's the price of the relay layer? What's the price of mining? There are actually problems with that, but like you don't have a market price for things. In Saito, you have a market price for transactions and propagation and data storage across the whole network. It's one fee. You don't need to worry. Like, I mean, you use Bitcoin, like Bitcoin fee estimation is essentially better.
Yeah.
But now we're introducing a couple of fees and separate fees and who's setting them in the market price. It's like, we haven't gone into how Saito solves this, but everything is actually a market fee because at every point in time there's economic competition. The block producers who you connect to, if there's someone who's pulling a ton of data and they're giving you no fees, well, that's the definition of a Sybil node, right? Is the Y? I think the Y's there.
Yeah.
Right? Like a Sybil node, people don't even really think about what a Sybil node is. A node that doesn't give value to the network. So it surrounds you and it can do various things. In Saito, like if you're surrounded by Sybils, and you know money is going to be coming in this direction too, right? Fees and transactions. You're going to notice because you're now half as profitable as you were when you were Sybil. And the people that are Sybil are either going to go into business, or they're going to take a look at their network and transaction flows, and they're going to say, look, this blockchain's not optimized. If we don't connect to these people, we're going to be a lot more profitable. And what that does is also means the usage is cheaper for users because the user can get faster confirmation and deeper block propagation. And you know, that's just a more fancy way of saying in Bitcoin and Ethereum, all of these other networks, there's literally, people say, oh, we want decentralization. There's no incentive for decentralization. And there's no incentive for network efficiency. Saito, at least, we incentivize both.
Yeah.
You know, if you value decentralization, you can pay a higher fee and your transaction will get deeper faster. And and the network itself will just eliminate the nodes that are useless. You know, like how do you justify, if you're a block producer and you're only connected to block producers, how do you justify that position? You've got to be a much bigger block producer who's producing blocks that the other block producers can't often do. But the reason they give you transactions is because this guy's terrified that he's like, well, if I give it to him, the transactions I have will be produced before the relay node, before the transactions that are copies of the ones that I have.
Yeah, because before somebody could give me these transactions will produce.
Yeah, because this guy's competing with other people. Like the dream for a block producer is to be the only one that has those transactions.
Yeah.
But if if they do that, their profitability goes up at the expense of the relay nodes. So the relay nodes, their economic interests are like, well, you know, and they don't need to broadcast the whole network. They can pick another block producer. Or, you know, maybe they have a long-term agreement where it's like, we're going to permit you to have this level of profitability because the blockchain does let you monitor it, right? Like you're going to be able to look at the blockchain and figure out very, very quickly, you know, what percent of the value of the transactions I'm sending
I
are
think
captured by me.
that's the key difference between trying to fix this versus what we have here is they're essentially the same intent.
Yeah.
But what you have to do is you have to make all versions of collusion make the network more secure and more efficient. In which case it's not collusion, it's just cooperation. The issue with collusion is that you have somebody's losing out from that. You're either losing openness or you're losing.
Well,
what's
going to happen? Like, what possible collusions you have is the same idea here. Like, let's say you have 3 big block producers, and they're like, well, yeah, we can. pretty much we can relay transactions, or we cannot, or we can not relay transactions and produce blocks ourselves.
Well, as long as there are valid transactions on the network, that's actually not possible. But like, look at this system. How do you even prevent this? We've invented a kind of network node, and we've just said, well, let's assert that this network node broadcasts to all miners. The economic incentive for that network node is not to broadcast to all miners, because this network node, well, it's getting paid, but if it can form a deal with two of them or one of them, if it can get away, it's got money. It's gonna. What is its incentive? Its incentives are not to actually do what we've asserted that it's supposed to do, and that's it's so much of what's happening in the blockchain space because of this. That people are inventing nodes on the network like archive nodes, and they're saying, okay, hypothetically, if this node does this.
Wait, just so I understand, you're saying his incentives will not be to send it to all of them, but send it to only one?
Well, you said, okay, well, the problem, the collusion, here's one hypothetical solution. I pay a fee to a relay node.
Yeah.
The relay node is supposed to send it to everyone.
Yeah.
But, I mean, why doesn't the relay node just send it to that miner and take the payment?
Well, it's the same idea, is because your transactions won't be confirmed fast enough, so you'll find a different relay node that does it.
So it sends it to two of the three.
Yeah.
Well, it sends it to two of the three. Now you've got, maybe it's going to 80% of the miners, but the miners are willing to pay something for it because it's not going to the 20%. Like, it's a fundamental incentive problem that's not solved.
But what, like here, let's say you have a kickback here that says, hey, if you don't send it to anybody else, I'll pay you some percentage.
Let's take a look at that.
That's exactly the right kind of question.
That's a fantastic question. Okay. So let's start with a single system. And we're sending transactions to relay nodes. And let's say the relay node is sending it to a single block producer. Okay? And the block producer says, if you only send it to me, I'm going to give you a kickback. So what you need for this to make sense is you need this to be profitable for the block producer. Or do we need it to be profitable for the relay node?
It needs to be profitable for for relay node, kickback is always profitable.
Well, if it needs to be profitable for both, actually, we've got a fundamental issue because the transaction has a fee of a certain amount. Let's say it's worth $1.
Yeah.
So how do we? Right now the nodes are being paid for the amount of work that they're doing. Like in a 2-hop network, let's say if it's $1 fee, let's make it. It's 10 Saito fee originating. So the first node gets 10. The second node gets 5.
Yeah.
The total amount of work that's done is 15. So the expected profits from...
This gets 10 if he produces a block and
No.
5.
No. This is a measure of work. This node has done 2/3 of the work. This node has done 1/3 of the work. Okay? So if he produces a block, he's still going to make 2/3 of the money. If he produces a block, statistically on aggregate, he's still going to produce 1/3 of the money. So this is how it works. Now, if this is under, let's say, the kind of the proof of work system, you're paid proportionally to the amount of work you've done. What Saito does with its routing algorithms is we're basically providing a way to securely and uncheatably generate work from your network routing. This is why we have cryptographic signatures. So what exactly are we thinking is going to happen? Because the way this guy makes more money is he says, okay, look, will you send it to me? If you send it to me, I've still done the same amount of work for the transaction. But because I can delay block production, then let's say the burn fee is here.
Yeah.
Because I can delay block production a bit, and I'm not that worried about competition, instead of producing a block at this point in time,
I'll produce it later.
Right? I'm going to produce it here. Or I'm still going to produce it at that time, but I've got some extra resources.
Yeah.
No. The amount of work that this payment describes is the routing portion. This portion is just given to the block producer right away. Now, what that means is this fee, where if the block is produced right at the line, this guy's going to get 10 Saito times 2/3. and this guy's going to get 10 Saito times 1/3, aggregate on average. As soon as we start delaying, well, all of a sudden, this is 8. And all of a sudden, this is 8 too, because a certain percentage of the fees is being eaten away directly by the block producer. So we get 8 times 10 to the 15 plus 2. How much does the block producer have to pay the routing node for this to be a good deal for both of them? And the short answer is it can never be a better deal for both of them because there's only $10. So you can't divide the $10 in a way that they're both better off. So the block producer, if he delays, he's delaying by impoverishing the relay node. So a separate payment to bribe, it works in the Bitcoin situation. It works in the Ethereum situation. It doesn't work in Saito because the payments are already optimized. The only way to make one person better off or worse off is to actually change the way work is calculated in the system. And that's a hard fork because it's algorithmic fork at the consensus layer. So side payments, I mean, you could do them, but it would either be less profitable for this guy or it would be less profitable for this guy. If the block producer tries to screw the relay node is going to be like, well, look, we've got an economy here. What the relay node is concerned about is he's concerned about exactly that. He's concerned on giving you the blocks, and because you're not moving as quickly as you can, you're delaying. And that's also where the meta efficiency of the network comes from, because, like, think, if there's not enough block producers, then if there's not enough block producers, the block producers can afford to wait because there's not a lot of competition. So the profitability for block producers comes at the expense of the profitability for the routing
routers. I see. Okay, that makes sense.
Right. So, like, if it's hugely profitable to be a block producer, the economic incentives are for people to set up block producing nodes because these guys are making so much money. It's like, look, I want in on that action, and then these guys go to these guys and we'll,
Right, or routers can just become.
Right.
Well, that's the real trick. Is this guy who's not getting good service always has the opportunity to say, "Well, I'm just going to hang on to all this and make the block myself." Then.
Right. And I mean, and the thing is, it works the same in reverse, right? And the way Seder does that is it's because you've always got competition between nodes in the network. So the routing nodes want there to be a lot of competition between block producers because that's how they maximize their share of the network. The block producers want maximum competition between relay nodes because, the block producers want to monopolize the traffic route because then there's a lot less competition. Like if this relay node is sending to this guy, he's got to be worried. Because the work that he's doing
maybe like
could be for nothing. If this guy produces a block that contains the same transactions he has, he gets nothing. So the entire thing basically
the other amazing thing is, depending on the quality of these two connections, it may make sense for this guy to send him these transactions as well, because he's going to be profitable if
that guy produces them.
Yeah, he's going to take a cut. So,
but he needs to use. This guy needs to use his do you merge? Like, let's say you have so it's A1, right? So you have A11, A12, and you have A13. Like this guy merges A12 and A3, or just use A12?
Well, look at it. If you're this guy, you've got a transaction that's made 1, 2, 3 hops. So if the fee is 10, it goes like 10 over 10. Like 2.5. This transaction is worth 2.5 over 17.5. This is 5. Like, it's just.
The only reason you would take this is that they're dribbling across this connection and then flowing.
Right. I mean, you might take it because, okay, well, most, like maybe 99% of this guy's transactions are coming from another source, and this is a one-way thing. Right? But like, the economics of the network also mean that the competition is between block producers that are competing for the same pool of fees. So you can have a situation where, like in the United States, setting up a network is super cheap and efficient. It's really easy, which means that these guys, and we can think of them like we're paying the peer-to-peer network in Bitcoin. No one knows how to pay it, while Saito pays for it. Like, it's so easy to do, it's super easy to find an access point, and the fees you pay are essentially the price of data. As soon as we have a system, like someone needs to walk across the border into Hong Kong, or walk across the border to North Korea, or like I'm an ISP and I'm literally rolling out fiber optic. There's no competition. Well, fees get higher. So Like,
yeah. The other key thing here is that you might, like, if you're wondering why that guy would send this on or why he never would, because of that halving, there's no harm in sending it here if I have
Yeah. Pretty much. If he produces, it's fine. If
Yeah.
Well,
that produces, better.
it just then that tends to
Yeah.
half.
Yeah.
and it's like note for like fast block propagation. We now actually do have copies of the transactions that share the network.
Just
But
send
I mean,
compact blocks. Yeah.
theoretically, what you get, like if we take a look at this, if you think of this as proof of work, I think it gets a lot easier because people are collecting work, but the work is worth different amounts. What makes work worthwhile? Well, what is really work is proximity to transaction flows, to transaction inflows, modified by your value collecting them. If you're the first guy generating use of the network, then in many ways you're the first person delivering the value of the network to the user. So the network stops valuing hashing. And what it starts valuing is give us money. And that's, like I would assert, that's the only value of work for any blockchain that's going to survive. Which is why we think Saito is such a big deal, because everyone else, they're like, well, we're going to pay for mining, or we're going to pay for staking, or we're going to create some really complicated thing, and then we're going to expect these cross-subsidies to happen. And then they get surprised because the cross-subsidies don't work because that's not what people are incentivized to do.
So far away. I mean, in Bitcoin they don't, but yeah, it's taking so far away. But anyway.
In smaller networks, they can because, well, bandwidth is free and storage is free. As soon as we're actually dealing with petabytes of data, it's like, well, you're not going to, like the peer-to-peer nodes in Bitcoin are not going to move exabytes a month.
Yeah. Cool. Yeah, let's talk about consensus.
Was there something, Richard, we were going to say about like the work fractions?
No, I think we got through that pretty quickly. Just the way that the decreasing fee value works. It's if you've got the spare bandwidth, you may as well send on the transaction, right? Because the benefit of having it included downstream is
better than zero.
Is better than zero.
Yeah.
So it's better to just at least get the transaction into another block if someone produces that block.
Oh, I know what I was going to say. I was going to say that one of the fundamental problems with Bitcoin and these other networks is because they don't fundamentally know what value is. For them, value is what you pay for. What you pay for is what you incentivize, and what you incentivize is what you get on the network layer. So that's why Bitcoin has tons of mining, and why people are like, there's all this value, but it's not going to.
So I think you can see here as well things like ISPs over time, as this group would be very much incentivized to say, hey, look, we're big transaction collectors. There's real value for us to put block creation right near where we're getting all of our main transactions because why not? Right? And so there's going to be a pressure between centralized infrastructure for mass transit and the localized infrastructure for the fee collection, and that's will presumably optimize to some level with the block producers moving as close as it makes sense to the end users. So the question of like how many people should be on the network isn't a matter of like technical design. It becomes an economic question of what's the best actual combination of ways to deploy the infrastructure we have.
It's also the network. I think maybe I think the point I wanted to make is that like you can note that the network is optimizing towards value because where does infrastructure get deployed? Infrastructure gets deployed where people are willing to pay fees to use the network. So it's kind of the opposite of a network that's designed to leech off of IPFS or whatever it is, because there you have a network that's designed to optimize around whoever will pay for the stuff you can get away with pushing and freeloading off of. That's not a scalable network because freeloading is not a scalable business model, right? What you've got here is you've got a network that's optimized. Like one of the nice things is who makes the most money? The person at that first hop makes the most money. So the network is optimized to push out applications. And like if you're building an application on Bitcoin, it's like, okay, you're paying the miners. If you're building an application on Saito, if you can build it so that you're the first hop, you're in a great position. I don't know what we're doing.
Well, I think we should, if we do more, which seems like a good idea, let's pause for a second and then, make a new file at least. So Check we're not going to run out of space. Because this is like an hour and a half.
Reward is actually which is not.
Yeah.
Block reward, you'll get block reward when you rewrite the history.
Yeah.
What you will not get is the transaction fees that
Right. And
actually you'll get something.
Well, you can, that is actually one of the problems. You can reverse the chain and steal the fees. Another example with proof of stake, this is like, it's a really common issue. We talked to somebody who's very well known in Silicon Valley about this, and they were like, well, Ethereum is secure because you need to buy up all of the tokens, and that drives the price up, which is the cost of the attack. Mm-hmm. And it's like, no, not at all, because if those tokens have any value, the amount of staking you're getting is paid for by the fees in the network. So, people are staking for the economic return, and what that means is all you need to do to attack the network is, just like Bitcoin, you invest at loss, or you invest at no expectation of profit. And what you'll do is you'll drive down the return, and then, by driving down the return, the people that are staking are going to go elsewhere, and they'll take their investment income earning assets and they'll sell them on the market.
Yeah.
So, the problem with that is it's just a fundamental misunderstanding of where security comes from in proof of stake. And
it's transaction fees.
Exactly,
transaction fees, yeah.
And so the fundamental question is not, do transaction fees secure the network? But that's what 90+% of people who approach proof of transactions, they get caught up in, because they're like, it feels insecure because Saito is secured by money. But they're like, proof of stake and mining, that's secured by something really strong. And in fact, proof of transactions is...
The security comes from transactions. There's an additional, what's it called? The security of rewriting history comes from transaction fees. The security of the, pretty much forking the chain or stuff like this, that's...
Well, I mean...
immediate forking, that's
you can put the transactions into your new block. So it's not...
No, but if you double sign the block, it will get slashed, it will lose all your money.
Oh, and staking. Yeah. No. I mean, that's a technical implementation.
Yeah. I mean, that's what I'm saying. There is different levels of things, and people think of them differently.
Yes. I mean, the fundamental point is that if you can actually rewrite the longest chain, what is securing that is fee production. Yeah. And that's people getting into technical issues of, you're staking, and then so, how dishonest can you be? Sure. I mean, the main point is...
Let's discuss the consensus. Yeah. Because if it's hour and a half already, that's... We'll need
it's filming now, so...
Where do we start?
First, there was...
We've done this once before, so...
I mean, let's just let's say we have a few block producers, and they're trying to agree on a block.
How about we...
on a chain, actually.
How about we start with what the user experience is and go into the network? And then we can talk about how we divide up the fees and what the problems are.
Oh, you want to start from the beginning?
I don't know, because we kind of did stuff before, so I'm just...
I mean, I'm thinking this might take a hell of a lot of editing, but we might want to edit parts of what we had then.
Yeah.
After this.
How about we explain the cryptographic signatures and we start from there?
Sure.
So the user
I think that might be a
transaction.
good thing to say. Look, to understand the consensus mechanism, you need to understand what it values, because it's not staking and it's not hashing.
Sure.
It's this, and then we go from there.
Okay.
I need to check in on end of day stuff.
Okay. Okay, so here's how Seder works. We've got a user, okay? And the user wants to connect to the network. So he connects to some computer in the network, and he makes a transaction. And the transaction is going to pay a fee. And the fee is going to be, let's say it's 10 Saito. We have another node. This node, it could be a relay node. It could be a block producer. If the user wants, they can send them to multiple nodes. And what's going to happen is, at this point in time, this node is generating work. Mm-hmm. And this work is the amount of the work that they've got. They've received it over the total amount of work that has already been generated in the network. Mm-hmm. So let's say this is a relay node. This guy doesn't want to produce blocks. So what he's going to do is he's going to forward it to another node. And let's imagine, for simplicity's sake, that this is another relay node. So this is a small town sending it to a bigger town. Not a lot of fees, not a lot of transactions. what Saito does, the first thing we do is that on the cryptographic layer, when transactions are sent around, the nodes that are sending and receiving, they cryptographically add data to the transactions.
This sign was very key.
They sign it, and what that allows us to do is cryptographically verify which nodes have been in. So I can't steal this transaction as a node over here. Like if it's produced in a block, I can't steal it as this other node and say, hey, I've done some work. Everyone can verify who's actually done the work collecting the transaction. So this amount of work now is 5 over, it's 5 amount of work. I'm going to get rid of the denominator for simplicity's sake. And let's say the routing node sends it again to a block producer. And this gets 2.5. So this guy is 2.5. So the thing we're doing is, if you can think of it as kind of a form of proof of work, where the work we're measuring is the work you've done taking this transaction and moving it into the network. So what we're really valuing is we're valuing fee collection. Collecting money for the network is the kind of work that we do. And the first thing I want you to notice is we're going to basically say, okay, so the total amount, let's say this guy produces a block.
Yeah.
So if a block is produced here, the payment eventually is going to be this. 2.5 over 17.5. And we're going to explain one of the challenges with Saito is other blockchains, the person that produces the block gets all of the money. And the result of this is that blockchain designers, they're focusing on making block production difficult or random, but they're really solving two problems at once. Who's doing the work for the network, who's collecting the money. What we're actually doing is we're separating payment for the work from the actual block production, and that's the difficult problem that Saito solves. The first thing I want you to note, though, is right away we've got an economic incentive for the network to work more efficiently. Because if this block producer looks at the transaction flow, why is he connected to this node? Why doesn't he just connect directly to this node? Because if he does, everybody makes more money. Right? This guy's going to make 2/3, this guy's going to make 1/3. Everyone in the network is better off because we've kicked out this node that it's not doing meaningful work. So the way you justify your existence in a Saito network is by doing work that's of value to the network.
That's something that nobody else can do.
Right, and the reason it matters is because the fundamental economic problem, if it sounds abstract, but what do we value? Well, the problems with Bitcoin and proof of work or mining and proof of stake is that the stuff that they value is different from the stuff that it needs to do to run the network. So what we're doing is we're turning payment for routing, and the data flows back the other way. But we're turning that into, because that's what we measure, that's what we encourage and incentivize. So one of the interesting things is the way you attack a Saito class system is you have to spend a lot of money. Just like Bitcoin, just like proof of stake, but the mechanism is different. So
what I'm really interested in is learning how, when you have multiple block producers and they're producing blocks, how does they agree on what is the latest block and pretty much what to build the next block on.
Okay, so let's take a look maybe at the network, and we've got, let's imagine we have a hypothetical network with, let's explain actually first of all how a block producer produces a block, and then we'll go to the network and we'll answer that question. Okay? So what happens is in Saito, we have something that's called a burn fee. And what that burn fee is whenever a block is produced, the consensus algorithms basically say, this is a measure of the amount of work that we need to include in a block. So you can think
of your form of work.
Our form of work.
Just to be explicit, yeah.
Well, you could modify Bitcoin to do this. Bitcoin has a flat work measure. You could.
Yeah, you can require those kind of.
Yeah, there are Saito class versions of Bitcoin where you can make the amount of work variable by pushing the work into transactions. We call that hash cache, right?
Well, that's what IOTA is.
Yeah, kind of. I mean, and the problems with that approach are you don't pay for the network. So you're back to square one. But yeah, so this is time, and that's work. And what you do is we set the burn fee, and the burn fee goes down over time. And what that means is that even if the network's not really being used at any point in time, and it makes it easier to attack, but you're never going to have a hash crash. So the situation in Bitcoin you can have where you have attacks on the networks, the mining power goes away, someone turns it off and thinks you got a hell and back. That never actually is going to happen in Bitcoin, in Saito, because if nobody produces a block for a while, it gets cheaper to produce a block. And what's actually going to happen is the difficulty of the burn fee is going to adjust upwards or downwards to keep block time constant. But what you have is, in any blockchain with fees coming in, we've got another curve moving in the opposite direction. And that curve is transaction fees. And you can think of this in Bitcoin because hashing is paid for at a fee, so there's some comparable thing. But what you've got is where those two curves connect is block time and cost of block production. So
in like this is also called like proof of burn, pretty much, where you burn some transaction fees.
We're not gonna one of the problems is that there are a lot of blockchains that talk about burning stuff. There are a lot of things where someone has a token, like you have to burn a lot of Bitcoin. It's very confusing. We call this a burn fee for a very specific reason, because what we've got is we've got a cost of attack. In order to do that, we've got to find a way to force an attacker. First thing to note is, let's assume if transaction fee volume goes up, it gets more difficult to attack the network, right? Because cost goes up. And we can actually adjust the burn fee to keep it constant. So an interesting thing is, if we can make it, in order to attack the network, they need to do more work and they need to pay more money. This is theoretically the same kind of security that we get in proof of work and proof of stake systems, right? Like the goal is we've got a cost associated with work and you've got to do more of it. So we're going to get to the same place that Bitcoin does, but we're going to need to solve a separate problem, because work is related to money. So the fundamental challenge in Saito is not how to make it difficult to produce blocks, because you can just spend money to produce blocks. As the amount of money that's needed to produce a block rises, the expense of attacking the network rises. There are actually advanced ways where block production can be a huge multiple of this. That comes at the cost of introducing a 51% attack. We won't go into it, but people should probably know that it's not as simple as you spend this, you attack the network. We can force this exponentially up. But the key thing to note is, here's the reason we can't do this in Bitcoin. It costs this much to attack the network. That's a form of work that's measured in fees. So in the Bitcoin system, we can't do this because it doesn't make sense. It's like, well, it costs you money to attack the network. We're going to take that money and we're going to put it in the block you produce. So when you attack the network, your attack pays for itself. It's kind of like you take all of the money, you charge someone $50 to open your door and burgle your house, but you put $60 on the desk. Like, your network's not going to be secure. Now, the way to make that...
I mean, the expense is like what you lose if you have mined on top of the chain versus like mining off chain.
The problem is...
Pretty much the expense is like while you're building this...
Yeah.
And I should use it the proper way. Like while you're building this, there's been built this, right? So the cost is actually missed opportunity.
Well, the point is that if all of the money goes to the person who builds a block, if they get their money back, there's no cost. So this is where the word burn fee comes in, right? Because if we take this money and we just burn it, then the network has the same security properties as Bitcoin.
Sure.
The problem is, if we burn it, if we start with 21 million tokens and we're constantly burning tokens, like...
You'll be out of tokens.
Well, yeah, you're going to have a different... Right. So it's like the network that can be secure, the problem is that we're making it useless. And, for a scalable network that we want to support itself, that's That's the issue. So it kind of feels like we're back to square one with Saito, because as long as we're destroying the tokens, we're secure. But if we do that, we've got a bigger problem.
Yeah.
So the first thing to note is there is an improvement here, because we've changed the problem. And we've actually stepped back to a problem that the original Satoshi team had, where there are kind of two problems. The first problem is, how do we make it difficult to produce blocks? Because if it's not difficult to produce blocks, everyone does it, right? But the second problem is, how do we make sure that the distribution of money into the system doesn't enable further attacks on the system? Proof of work solves this by centralizing things in the hands of miners. It says, if you produce a block, we're going to give you all the money. But we know the payment's fair because block production is essentially random based on hashing. So the qualities that we want out of proof of work, which is that it's difficult, which is that you make proportionally the amount of money that you're doing the work, those properties in Bitcoin, they create certain problems because they force us to give all of the money to the block producer. In Saito, well, we've gotten rid of that, but we've introduced a secondary problem. But we still preserve difficulty. So the challenge shifts, and the challenge isn't how do we make it difficult to produce blocks. That's proof of work, that's proof of stake. They're introducing these side activities that are difficult and that have their own properties and that essentially are attackable with money. People try to pretend that they're not, and we have a separate problem. And the separate problem is, okay, we're charging you money to produce blocks. We want to pay you for the work, but we need to find a safe way to do that. If we can find a safe way to pay you for the work, then we have these security properties. The problem is, if we're paying you, how can we pay you for the work in a way where you can't do what we like to call we call it a fee recycling attack, right?
Yeah, you just take the same thing, so you do it without one transaction and
so
money from the exchanges.
Right, like if you can collect 100% of the fees, you build a block, you collect 100% of the fees, your cost of attack is the cost of producing one block, and then you get all of the money back. This is why it's one of the reasons Bitcoin has 51% attacks, because if you produce a block, you get all of the money. The solution to this is, well, what if we can find a way to guarantee that you can't get 100% of your money back? What if you could only get 50% of your money back? Would the network be secure? And the answer is, well, we could figure out what it costs, because now our cost is no longer this, but we still have a cost of this. And this is kind of the property of, it's the security property. It's fundamental to Bitcoin, but it's also fundamental to Saito. Because in Bitcoin, you say, well, it's the cost essentially of renting 51% of the hash power, or building that, which is the cost of attack. And what Saito says, well, the cost of attacking the Saito network is whatever percentage of money you cannot recover. Right? So the security challenge is different. It's producing a block is easy if you're willing to spend a lot of money. The challenge is, how do we make it so that you can't get your money back?
So just for me to understand one thing, if I'm a block producer, right, so I have some amount of transactions that I collected. So this transaction, they pretty much say, who am I, right?
They say who you are.
The receiver of the transaction, so you can actually validate this, like I actually received this transaction, so didn't like steal them.
So like, and if an attacker, it's one of the lovely things, if an attacker produces a block, well, there are two things. If they put all of their transactions, if they steal transactions from your block and put it in the network, you actually still will potentially get paid. So if an attacker attacks the network, there are two things they can do.
I have a specific question. So I produce this block, then I myself actually trying to produce block with, let's say, I just kicked out one of the transactions.
You mean you want to produce?
I want to produce exactly the same, same parent, two different blocks.
If you want to,
So what's going to happen in this case?
Maybe we can kind of explain how it works before we get to that.
Okay.
Basically what it boils down to is nodes are positioned in the network. And the flow of money comes into them from the transactions filtering into the network. So if you really want to cause problems, what you're talking about is a block flooding attack. And then the question becomes, how does the network deal with block flooding attacks? The most damaging thing you could do is try to encourage a lot of other people on the network to produce blocks simultaneously.
Well, I mean, this is what the most damaging thing, because this transaction is sending money to exchange, and it's not here.
Well, here's the thing.
I mean, this is literally what double spend is.
You've got, well, no, I mean, the double spend isn't the problem, because the cost of block production, you determine what the cost is. Now, what that's saying is that's saying for you, for your specific node, that has the potential to produce 2 blocks, right? Now, the cost of the block for you depends on the cost of producing the block. The fundamental property is that if you're an honest node, and you're generating work where the fees are coming from other people, it's essentially free to produce blocks.
Yeah.
If you're that node, you're saying, look, I'm an honest node, I'm capable to produce a lot of blocks, but it's like if I'm swapping out one transaction, say. Well, if you're swapping out one transaction, then the cost for you of a block flooding attack would be that one transaction.
No, but let's say, I mean, most of the transactions have the same fee, so...
You're saying I'm a block producer.
Yeah.
And
I created 2 blocks.
you create 2 blocks that are off the same parent.
Yeah, and I have exactly the same amount of fees, just one transaction swap for another. One of them sends money and another one doesn't.
Yes. Well, there's 2 questions. The first question is for the user who receives it, and the second question is for the network as a whole. Now, for the user that receives it, it's just like any other blockchain like Bitcoin, right? If you want security, security scales with the number of confirmations.
Sure.
And so if you are making a payment to me and you're a block producer, the cost of attacking the network is different for different nodes in the network. So if Google is producing 30% of the blocks, their cost of attacking is a lot higher than someone who doesn't have that inbound transaction flow.
Maybe a lot lower.
Well,
because they have.
Here, it's kind of getting to the central attack, because you're jumping to the attack vectors, but that's fine. The point is, if you're an honest node, what are you doing? You're helping users take their transactions, which have fees, and you're moving them into the network, and that's the measured form of work. If you're an attacker, well, you can fake that. How do you fake that? You fake that by making your own transactions that pay.
No, you can also just do, you can be an honest node today, and then you do the work that you're supposed to do, and then tomorrow you decide that for this specific transaction, you're not going to include it.
Yeah, for sure, of course. What you're doing is, I'm not worried about the confirmation stuff, because it's kind of like, well, for a user accepting a transaction, what we've got a system that says producing a block for various people has a cost.
Yeah.
So if you're paying me a 15-cent transaction and the cost of a block production, like...
So my point here is that when you're saying that producing a block costs, so in proof of work, for example, you will need to pay here in work twice. Right?
Yes.
Like you'll spend time here, and you need to spend additional time.
Yes.
In proof of stake, you will be actually slashed right away, and none of these blocks will be valid.
Yes.
If you show them both. In your
this is a block flooding attack.
Yeah.
Now this is possible. It's not economically incentivized, and the network incentives actually. What basically happens is the consensus layer says if you've got a relationship with other nodes in the network. So if you produce one block. If you produce another block, you can produce 10,000 blocks if you want. You can send them to your peers.
Yes.
Your peers are not going to propagate anything past the first block. If you want your peers, by consensus, if you convince them to, they can. Protocol doesn't do it. If you want them to propagate, you've got to create the longest chain. So if you want to actually have a block flooding attack and you want it to propagate through the network, it's a lot harder than you think. If you're just talking about confirmations, like a double spend, the answer to that is we calculate the cost of the block. The cost of the block depends on whether you're attacking it and how many transaction fees you have from other people. And you take that cost and you multiply it by the number of blocks, and that's your security. And that's the same as in Bitcoin. If Bitmain has 49.9% of the network and they only need to do a tiny bit of work, well, what's your security against Bitcoin? It's cost times blocks. The block flooding attack is the more interesting thing to think about.
So Okay, I mean, let's just to finish this thought. So let's say you send this to node number 1 and this to node number 2, right? So you send to different nodes, different blocks.
Yeah.
So how does this nodes?
Well, as you're going to see,
Like pretty much, my question is why will this not pretty much why would different N3 and 4, right? Why would not they split up?
Well, the question with that is okay.
You said yourself, right? It will only accept one block from the guy. So when this guy will broadcast even this block, he will not accept it. And the same way,
the cost of attack scales with the number of blocks. The same money can potentially be used in different chains. Yeah. So there are two questions here. The first fundamental question, which is the security one, is noticing that we're providing the same security as Bitcoin and these other networks in the sense that you can calculate the cost of attack on any chain. So there's two questions here, and it's important not to dance between them. There's how many blocks do I wait for confirmation?
So, let's forget about confirmation. I'm asking you, I as a malicious node, which have transactions, so it costs me nothing.
Yes.
Produce 2 blocks.
Okay, so
with different thing, right? And it costed me 0.
Well, no. It doesn't cost you 0.
I lost whatever. Half of my money as usual.
Let's put some numbers on it.
Okay.
So the cost, let's say it's $10,000 per block.
Okay.
And remember that there are defenses that can exponentially increase that. So that it can go up to millions.
Just so I understand, the cost of the producing block is 10,000.
Yeah.
I got 10,000 of transaction fees in this block.
So you've done the work of the network of collecting $10,000.
Yes.
Because of that, you can think of it as a discount on the work that you're doing.
Yeah. So I've got this transaction.
Yes.
So there's one transaction that's can pretty much.
Well, you've done the work, so you're entitled to it. This is not the question. I mean, there are two.
So how much am I spending here? If I collected 10,000 transaction, worth of fees.
I mean, we haven't got into actually explaining how the payment mechanism works, but if we're talking abstractly, let's say, let's just assign a figure out of the blue and say, if you spend a ton of money, you can get 50% of these fees back in your pocket.
Yeah.
Okay? So in that case, the cost to you of this block is not 10,000. The cost of this block is 5,000. Okay? Sure. So you're getting 5,000. This block is going to cost you another 5,000. This block is going to cost you another 5,000, and it's the same here. Now, your initial payment, if you want to attack the network by doing a split like that, you can. It's a block flooding attack. But on this chain as well, if you want to do it another 5K, you want to do another 5K, you could create a third chain, and you could try to get the network to accept that as well. And we're saying that the cost, meaning the amount of money you lose, if you work really hard and you manage to recover 50%, and that's not actually viable. But what you could see is that whatever chain you try to maintain, we're still maintaining the properties that on any chain there is a cost to the length. Now, the question, so for users on the longest chain, we still have a guarantee of what it costs you to attack the chain. So in that sense, it's just like Bitcoin. That's like I can rent hash power and whatever the longest chain is. The attack here that matters, it would be the block flooding attack, which would be, could I use this to produce 50 different blocks that would saturate the network and cause the network to fork out on 50 chains, and there would be so much buffer back and forth that it would be a problem for the network.
Well, I mean, this is interesting attack as well. I'm like, the kind of main side here is I always get only 50. If I did not do this, right, I get 5,000. So
No. What we're doing is I'm trying to separate the fees from the cost to you. We're saying is if you remember.
I'm producing blocks. What is the cost to me?
Well, what you need to do, if you remember, is all of the nodes in the network are competing together, right? So if you're an attacker, let's take a pure example, you're not doing any honest work. So the cost to you is generating the amount of work that the network considers valid. It's like Bitcoin. There's a cost to producing a block. We can measure the cost of producing blocks. So for an attacker, it's like renting enough hash power to produce a block in Bitcoin.
But let's say I am doing, like, in your definition of work, which is collecting transactions, I am doing the work.
Okay, so you're an honest node on the network.
Right, I'm an honest node on the network,
okay,
which I'm not, but I'm not. I actually have modified client.
Yeah, I know, but there's a rhetorical slip here. You're saying, I'm an honest node on the network. Honest nodes on the network. Can I still yours? That's kind of honest nodes on the network. Let's say you've got a China node, and you've got a US node, and let's say you've got a Europe node as well. Now, if you remember, the burn fee is adjusting to the pace of block production. Now, the US is, let's say the US is generating 30% of transaction volume. Let's say China is generating 30% of transaction volume, and let's say Europe is generating 30% of transaction volume. What we're going to see is that the US, okay, it's an honest node and it decides to attack the network. Well, the US has 30% of transaction volume, and it's going to essentially, so let's say it produces the first block for free. So this is a US block.
Yeah.
Now,
so now at this point it does two things. It first of all produces another block, which is exactly the same block.
Sure. This is a block flooding attack. This is not.
I mean, like the block flooding is a little bit more. I think like what you described a little bit more complicated. I have a very simple question. So I produce two blocks, and I literally send them to two. Like the block number one was sent to Europe. Block number two was sent to China. Right. So now China sees this block, and let's say Europe even like transmitted the block it received from US to Europe to China, and China declined to use it, right? Because it's a second block.
You got two blocks.
Yeah.
There's China and Europe. Think of Bitcoin. So we got a Bitcoin fork here.
Yeah. So we have China and we have Europe.
So forget about Saito.
So in Bitcoin, this have taken, let's say, 10 minutes, and this have taken 10 minutes. Actually, in Seder, right? As far as I understand, this did not take 10 minutes, right?
Yes.
Like I just produced it immediately. Two blocks.
It's a block flooding attack. Here's the question. What I'm trying to do is I'm trying to get you to see that the block flooding attack in Saito is different than work difficulty chain confirmation, because each of these forks there's going to be a cost, because there's a cost of block production. So you can spend the cost of block production, and sure, you can produce any number of chains. What's actually going to happen in the real world in this situation is the US is just burning its reputation. No one's going to take its block seriously, and if it becomes a problem, China and Europe are going to start coordinating on things. But think of in the Bitcoin proof of work example, where let's say these are two blocks that are produced by two people. Who produces the next block? Well, the US has produced a block, and it now has zero work.
Sure.
So if the United States wants to produce another block on either of those chains, it needs to pay out of its own pocket.
Yeah, so I'm not talking about this. I'm talking about now China and Europe produces their blocks.
Well, who produces the next block?
Well, let's say China produces the next block.
Well, whoever produces the next block is whoever is profitable for them to produce the next block.
Well, let's say China produces the next block, right?
So China produces the next block.
And then let's say Europe is actually producing the next block.
Okay. Europe builds off the longest chain. Why would Europe build off that? This is Bitcoin. You have two nodes that produce a block, and then someone builds on it, they propagate, and Europe does it too. I mean, if you're describing a model of the network where the US can send data to China and the US can send data to Europe and the network doesn't ever communicate, that's like a version of Bitcoin. It doesn't make any sense.
No, but you said even if they do communicate, you kind of decline the second block from the same entity.
No. We're saying that there's a certain cost to the United States in producing blocks. If the United States wants to continue to produce blocks on both chains, it can. The point is that it will cost it money. The key point is that attacking the blockchain costs money. You can't. You're forgetting that there's a cost to the attack. If you're willing to spend the money, yes, there is a cost.
But this is because you're saying attack in a way when I produce blocks pretty much that are empty.
What I'm saying is you're mixing up you're mixing out an attack on the longest chain. Because on every blockchain, in every blockchain...
So this is different. Like, I understand that producing empty blocks when you don't have transactions is an attack that costs money. I totally understand that.
Okay.
Because, yes, empty blocks, because you don't have transactions at this point, it will cost you money. The part I'm trying to figure out, which I'm like...
Maybe think of it this USA, USB. This is Bitcoin. Other people on the network will build on the longest chain. So what I'm trying to get you to see is that there are two issues here. The first issue is if the US, like China and Europe are going to build on what they think is the longest chain.
Sure. Yeah, yeah.
So if it costs the US money to produce blocks, the US can keep it, like China and Europe can do this, and then the US produces these blocks, right? Okay, and then China and Europe actually...
Well, so the question is like US can do this, right? US can do this, and Europe will produce block here.
Yes.
And then US will do this. So you actually need...
The U.S. can keep doing it if it's willing to pay money, but like this is exactly the same in Bitcoin as the U.S. just producing a single block. Like you're kind of creatively coming up.
I agree.
You know, the fundamental thing to notice actually is, and this is where it's a radical improvement over Bitcoin. Note that in Bitcoin, in Saito, you've got to, in this kind of situation, the U.S. needs to pay 100% of the cost of producing a block. In Bitcoin, the U.S. needs to pay 51%. So there's actually something really interesting. People have difficulty with it, and I think the reason people have difficulty with it is why the block flooding attack is more interesting. Because the block flooding attack is more interesting. People have they cognitively have difficulty wrapping their heads around it because what Saito does is it puts a price on attacking the network, but that price is slightly different for everyone else. So, if Bitmain is producing 33%,
it's 70% on top.
Like the security question becomes, how do we make it so that Bitmain can't collect its money back? And there's another really lovely property of this, which is, let's say you're the US. Because basically what happens is you can take other people's transactions into your blocks. You can steal them. If you do that, though, the people that routed, your ability to get the money from the block shrinks. So if I'm an attacker on the network and I put 100% of my money in the network, the challenge is maybe there's a way I can engineer to get 50%. If I start including transactions that were included from China and Europe, well, I can do that. But then I can only get 10% or 5% back. And so what you get is you get a situation where the US, which is trying to attack the network, say, we're in Beijing, so of course, if the US is pulling out this attack, it's got two choices. One, if it doesn't include any work from Europe and China, what happens is the amount of work on the network that's outstanding, that's not in the longest chain, starts going up. And what that means is, as the burn fee adjusts, like at every point in time, at any point in time, China and Europe can dump their transactions on the longest chain. So the US has a choice. If it's trying to censor the network, it needs to keep producing blocks, and the blocks need to have more and more work, or China and Europe at any point say, well, we'll put it there. And the US says, oh no, you can't put it there because I'm producing this next block. And then they say, well, okay, we're going to put it here. This is actually, it's really interesting because in Saito, what happens is the fact that the work can be transferred between chains like this eliminates the 51% attack in an interesting way. So there are other options here. The costs to the US go up because, one, they have a choice between they include the other transactions, right? So like they steal the transactions, like China produces a block here, and the US says, nope, your transactions are here. If they do that, they stop being able to capture 50% of the money because the transactions that they include force the money basically to other nodes in the network. So you can either have help producing the longest chain, you can either stop work from building up outside your chain, or you can include it. But if you include it, your ability to recapture the money goes down.
Yeah, instead of like 50%, you get 40, 30.
Right.
Yeah.
So, I mean, the two general problems, or not problems, but kind of the cognitive things getting people to think about it is every blockchain is secured by fees. What we need to do for maximum security is we need to have a blockchain that can process massive amounts of fees. That's what we're building, because the biggest blockchain is going to be the most secure one because it's going to be the most expensive. But two, notice that the difficulty is different. It's like, yeah, you can produce it. The challenge is this: how can we lower it below 50%? Mm-hmm. How can we keep people from recycling? Because what we don't want is we don't want a system where the US does this and then it starts recycling its fees into subsequent attacks. So how can we do that? That's actually the real question.
And also, where does the other 50% go?
Well, let's get into that.
Yeah.
Right? So if you remember, we did this kind of, maybe just first with the block flooding. Mm-hmm. What you've got, and you've got a massive network processing terabytes or exabytes of data. You know, if you're a node, you're collecting honest transactions. Mm-hmm. One of the lovely things is if you start attacking the network, the easiest way for the network to respond is we stop sending you fees. Yeah. So you can subsidize your attack with honest work, but like if I'm a user and all of a sudden you start creating network disruptions, the first thing I do is I send my transactions to someone else. And remember, if you're like the US, if you're Google or something, and you've made massive investments in internet infrastructure in order to process Saito class blocks, and all of a sudden like people stop sending you transactions because you're attacking the network, like you're kind of screwed. So the economic incentives, like you could try with the block propagation thing. One of the major differences is that the incentives on the rest of the network are, one, people stop sending you transactions. Two, at massive scale, you don't have a network structure where it's not hub and spoke because Google is connected to everyone, so Google can't even pull it off. Because the main block producers can only maybe manage connections to 12 or 13 other nodes, given the limitations of the pipes. Anyway, we were going to talk about how money's divided up.
Yeah.
So the key observation is, well, we're going to divide up the money, right? And notice that we had, we previously did things where we said, like, you know, this node's going to get 10 over 15, and this node's going to get 5 over 15, right? What happens, we mentioned the burn fee before. So as soon as a block is produced, the burn fee is really high, and then as time passes, the consensus algorithm lowers the burn fee. At a certain point in time, someone on the network has enough work in their mempool, they're able to produce a block. This is where the fun begins. Before we do it though, now is the time to step back to your question, why isn't everyone producing blocks at once? The reason is, transactions and fees are flowing into the network. Work is flowing into the network at different places. So if you're the United States, you're going to have access to American transaction flows. If you're China, you're going to have Chinese transaction flows. Singapore will have Singapore transaction flows. And what's going to happen is the network will adopt an organic round-robin production system. Because as soon as the US produces a block, well, the amount of work it has in its mempool goes to zero. China's still got blocks. Singapore still has blocks. And so while the United States is building up work to produce another one, well, these guys are going to produce a block. And the network basically eliminates people who are in close proximity to each other, who are producing blocks for the same transaction set. But anyway, let's move on to the question. So we've got basically two kinds of payments involved in the production of a block. You've got routing nodes. This thing below the burn fee. This is, we can think of it as a routing payment. So this amount of money is going to go for routing. If there's a lot of block producers, and there's a lot of competition for block producers, remember the routing nodes have an incentive to give multiple block producers the transaction because they want block producers to be producing as soon as they possibly can. The reason for that is if a block producer can afford to wait, if it can make a block with this amount of this amount, well then this goes directly to the block producer. So if a transaction pays a fee of $10, in this example, maybe $7 would be divided up between routing nodes, but $3 goes directly to the block producers. And what this is doing is it's creating competition between block producers and routing nodes where if, this is going to be divided up, but if it's really profitable to be a block producer, that's going to happen in situations where there aren't enough block producers, right? Like the blockchain is really big. You need to make a real investment in Google scale infrastructure. You need to have like a connection to level 3. Like it's super profitable. You can afford to wait. What that means is it's a tax on the fee. So the block producers get their money right away. And the economic incentives plus router behavior is going to keep that at what the market prices are basically, because there's a return on setting up a block production facility. So that basically gets taken off right off the top. It depends on the degree of competition between block producers, right? So here's the security. The security question is, how do we divide the routing payment, right? Like, what we do is we have something in the network that's called pay split. Pay split is a variable that goes between 0 and 1. When the money is at 0, it's going to go to a routing node 100%. When the variable is at 1, it's going to go 100% to a group of nodes whose purpose is to hold a lottery. And what's going to happen is we're separating the act of block production from the act of deciding who gets paid. So if we go back to the Bitcoin example, the act of producing the block is the act of getting paid. It's not that way with Saito. So if the pay split is 50% say, because we can do dynamic pay split later, but let's start with static. So if the pay split is 50, the cost of producing a block is 100, let's say, plus whatever the block producer surplus is, but whatever. You're going to get, if you're a routing node, you're eligible for $50. If you're a lottery holder, you're also eligible for $50. This is, in the consensus rule, it's a variable that's managed in the consensus network. So you can't attack the network and suddenly change the pay split. We can go into that. So how does it work? A block is produced. And the block itself, in the Saito implementation, you could do like an algorithm random stuff. We use mining for a couple of reasons, because it's simple. And what you do is the block basically has a hash. And the block implicitly, the hash of the block implicitly is something we call a golden ticket. Think of like Willy Wonka and the Chocolate Factory. And the routing nodes and the block producers produce a block. As the block is propagated, the golden ticket is available for everyone on the network to look at. And right now it's a mining puzzle, simplicity's sake. And if a lottery holder finds a solution to a golden ticket, what it does is it takes that solution and it propagates it to the network in the form of a transaction. And that transaction, if it is included in the very next block, the lottery holder that found the ticket gets paid, and a variable that's associated with a solution. And because it's a cryptographic puzzle, it's guaranteed to be random. That random variable picks which of the routing nodes contained in all of the transactions in the previous block gets paid as well. So, and it doesn't need to be 1, we can divide it between 10. The main point is that the randomness from the lottery is used for the distribution of money.
For this or
for this.
For this.
Right? So remember, the distribution of money here for the block producer is, it's 10 over 15 and 5 over 15. So for a 2-hop production, the block producer can it can expect not a 50% payment, it can expect on average to get 33% of $50 equals really not very much money. What is that? That's like 17.5. Okay. So you notice in the earlier examples, we're talking about $50. In a network where the block producer is 1 hop away from every transaction, they're in fact going to capture, with 50% pay split, 17.5. So the cost is going to be 82.5%. right? Mm-hmm. Now, in a network that's actually more distributed as real-world networks are going to be, the cost of attack for block producers is going to be higher. And the question you've got to think about is, well, we've also got a cost of attack from mining nodes as well. And this is the nature of what Saito does. Saito says, look, the solution to the problem is we can make the network secure on fees alone if we divide up the fees. Mm-hmm. And the challenge becomes, how do we divide up the fees in a way that we can actually calculate what the cost of security is, mm-hmm. right? And this is the other thing, like remember, because we've got a mining puzzle here, producing, you're not making 50% in profit. If you produce a block, if the next block is produced and there's no solution, nobody gets paid. Mm-hmm. So in addition to generating an attacker, in addition to generating the money for the transactions, it needs to come up with the money for the transactions. It also needs to be in a position to determine the lottery. Mm-hmm. And you can think of the lottery position like validators in the sense that, if you've got the US in our earlier example, which is trying to rewrite the longest chain. Yeah. I mean, in order for this to be a low-cost attack, it needs to be able to source transaction fees from the entire network. Mm-hmm. And when that happens and it tries to attack the network, people are going to be like, well, I'm okay with that, and they keep paying for it. Mm-hmm. You've got the lottery holders. It can be a randomization function. It can be mining, whatever. They've also need to continue to mine and hash on this, because if they don't, the U.S. can't recycle any money. Mm-hmm. So if
U.S. can, so only lottery ticket holders can mine.
If you don't, anybody can mine. I mean, in the mining,
the U.S. can be mined.
The U.S. can mine too. But notice, if the U.S. is mining too, why don't we get to it a bit? But note that they're not making $50 because the amount of profit that they're making from this. Mm-hmm. The profit for lottery holders is actually driven by market forces to be exactly the same for the profits for routing nodes. Mm-hmm. So if you get $50 back, well, they probably need to be spending $48 to $49 just to do that. So an attacker that needs to co-opt both, well, if you're using mining to attack the network, mm-hmm. It's only really feasible if the profits from mining are way higher than the profits from routing. And kind of vice versa. But this is dynamic pay split. The example we're talking about is just we're saying, okay, there's 50%. Mm-hmm. The main point is that, no, if the transaction is not solved, if the attacker is just trying to use money, what we've done is we've introduced a cost-based system that means it's no longer 5,000 per block, right? It's 5,000 per block. Like they're getting 17%.5 plus that's their profit, and they need to spend practically all of this. So otherwise, the amount of money that they lose starts going up. Mm-hmm. And what this lets us do is it lets us calculate. You can calculate the cost of attack to various people in the system. This is sort of the first version with a fixed pay split. Mm-hmm. We have a version with a dynamic pay split, and what that does is it changes this so that the profits from routing and the profits from mining are driven by market forces.
Yeah, that makes sense.
The first version is just like thinking about this. Mm-hmm. One way to think there is a difficulty to mining, and let me maybe explain a bit because it's lovely. We basically let the miners vote on what the difficulty of the puzzle is. Mm-hmm. Now imagine with a 50% pay split, what's that going to be? Well, the miners vote by providing solutions, mm-hmm. and the miners have an economic incentive to move difficulty to the point that there's one transaction on average per block.
Yeah.
Right?
So like if there's less, right, you reduce the difficulty. If there's more do you include multiple transactions?
Mm-hmm. No, you can't. You can only include one. And there's a lot of security benefits. Like one of the things is if you're attacking the network, you need 100% of the lottery mm-hmm. to pick yourself. It's also like it's the reason why if you copy transactions from other blocks, well, you can't control what the random solution will pick. Mm-hmm. So the attack that we need to solve is like in the Bitcoin attack, you produce a block. Well, thank you for all of those transactions. I've got more mining power. I steal them. I put them in my block. I get paid. In this, if you produce a block, I steal those transactions. It's increasing the cost of the attack. Mm-hmm. So, but note, like there's lovely properties with difficulty where if, like this is at 100% of the difficulty. But notice things like variance. 100% of difficulty is going to have some variance. And if you're an attacker, producing more than one doesn't do anything for you. There's going to be some variance in golden ticket solution as well. So it's another security thing, because if you produce two solutions and you're attacking the system and choosing yourself, that doesn't benefit you at all. But the variance above doesn't give you any benefit. So the variance below only imposes costs. So even an attacker that can match 100% of the lottery is still going to lose money just from statistical variance in the scale of the mining solution. Anyway, that's basic Saito, which is that you divide up the money, you introduce a system of generating a random number to decide who gets paid. The attackers can't cheat without incurring additional cost. And you use that to basically say we have the properties of Bitcoin, which is there's going to be a cost for producing certain blocks on the network. And then the larger economic scheme is saying, if you're an honest node, you're collecting genuine transactions and sharing them with friends and then other nodes on the network. If you're an attacker, because everyone who's doing anything at scale, it's their entire economy. Like, no one is going to be, if Google is producing 20% of the network, if they start misbehaving, the economic incentives for everyone is literally to behave in a way where Google's cost of attack goes way, way up. We stop sending them transactions. The miners they're like, look, you're destroying the network. We're making money from this. We're not going to support you. And basically the whole thing means that the cost of attack is honest nodes do work, routing work, and they get paid for free. Dishonest nodes, they have to attack the network, and it's not just 50%. It's like, because it becomes exponential, because if you don't include other people's blocks, the amount of work that is building up outside of your network, waiting to come on at any point in time, grows to the point where the amount of money you actually need to spend, not only does the cost go up, because you recapture less of it, but
so when you're choosing between two chains, right, do you use amount of kind of transaction fees that are in each one?
It's basically, you need to rewrite the longest chain, you need a higher difficulty, and you need the longest chain with accumulated work.
But you mean the amount of fees accumulated?
Accumulated work. Work is.
The fees is like.
Work is a measure of fees with the efficiency of the network. Yeah.
Okay. So one like the problem is. One problem in proof of stake is, without slashing, is that people will just build on both chains, right? Yeah. So the same question I was asking before, where US sends, both chains to everybody. Why would not Europe?
There's a cost to producing every block.
No, but like you have, this is US, and this is Europe, and this is China, and they're just doing
that's like a Bitcoin fork. Like any blockchain, you can have a fork, and the question is, where does the rest of the network build off of?
No, but this is free for them.
Well, you've got a fork.
It is a fork, yeah. So the question here is that it's just, in proof of stake, this problem exists is that. You will, as a validator or block producer, you really don't care which chain to build on. You will build on all chains.
Here's the thing: you've lowered the cost of the U.S. in this situation, unless it's ponying up cash out of its own pocket.
No. In this case, it's like literally. Let's just imagine this is the same blocks.
Yeah.
Just there's one difference here. That's all.
Yeah.
So Europe and China, they're actually not they're not malicious. They're not malicious.
Yeah.
They're just not really following the protocol. They're just well, why not? Well,
you can have an easy fix for this, because the hash of the blocks is going to be different. You just have a consensus logic that says which one are you going to favor. You favor it by something entirely random that's not controllable by the U.S. Right? Like what you're saying is the attack that I envision is that all of the core nodes in the network will build off all of the possible forks.
Yes.
And well, look, we're talking about a blockchain that's moving petabytes of data a day because we're actually paying for the network. I mean, first of all, I don't think that's a realistic issue because the economic incentives for everyone who you've got an attacker, the economic incentives for everyone is like, well, look, there's an attacker. The real question is, to what extent
they don't really care, right?
Well, they do, because if the network becomes useless, they're not going to get paid. That's like saying, look, everybody will kind of mine separately on things and off. Why don't I have 500 blockchains? If you want to use Bitcoin, it's like, well, which chain do you want to transact on? I'll broadcast your transaction to all of the forks. I mean, I suppose it's a theoretical problem, but
it's mostly a question of would people modify their clients just in case to make sure that they get included in those?
Well, I mean, the thing is that
or they can lose their.
Sure, but one of the differences is you say, well, what is the network structure going to look like? You're going to have a series. The bigger the blockchain gets, you're going to have a series of people that are specializing in infrastructure, right? You're going to get, Google in the States, Baidu in China. It costs a non-trivial amount of money to be running a network.
Sure, yeah. I mean, if we're assuming that, the people invested a lot, I mean, that's the same as ASIC assumption, right? People will not attack the network if they bought ASIC because they bought ASIC and they don't want to, this is some cost for them. They don't want to pretty much attack network because otherwise they will lose their.
Well, it's interesting because that's in the white paper, but I don't think that's. I mean, the thing is, there's a profit motive. It's not a sunk cost motive.
I mean, it is sure, but it's a profit motive for ASIC as well. Why would you attack the network if you already?
It boils down to assumptions of economic rationality, right? But that's also in Bitcoin, you're expecting people to rationally mine on the longest chain. This sort of thing, if you throw out the expectation of economic rationality, I mean, there's no guarantee what chain people mine on anyway.
No, but I mean, this is economic rationality. I will be putting blocks on all the chains that I see because there's no reason why not.
Well, you're going to no, there is a reason why not. And the reason why not is that we're operating at scale and big blocks have cost. This is not 2009.
Yeah, sure.
It's not 2009 Bitcoin.
If we're assuming there's only a limited set of people that can produce this blocks,
we're designing the economics of the blockchain to support actual scale.
Yeah.
So people, in 2009 Bitcoin I can do this. It's but we're not talking about a megabyte every 10 minutes.
Yeah.
We're talking about. I mean, right now we think the limit's about 100 terabytes, but it will be in the petabytes. Now, what you're going to get is you're going to get these core nodes in the network. And because we pay for routing, what you're basically doing is you're creating an economic incentive where, different regions, there are kind of routing nodes, and the routing nodes will connect to maybe one or two.
How long do you expect propagation take from?
Well, what we know is that the network has economic incentive towards efficiencies, and we'll see. What I think is going to happen is I think that if people can't keep up with the main network, right now it's 30 seconds. I mean, it could be 2 minutes, it could be 10 minutes. If people can't keep up with the big network, the way to do it is as a routing node. Because why do you run a routing node instead of a full node? It's because your network can't actually handle the bandwidth. So, and then the routing nodes, there will be users that will connect to those. But, why do you want to pay for the routing nodes? The network structure, basically, you're going to have a core group of people.
Nodes, yeah.
It's like level 3, This attack is kind of like level 3 communication starts screwing around with packets for its customers, right? It could happen, but if this, it could happen. But look at it. What actually happens if this guy starts screwing around with the network?
Well, if you guys controlled by Russian government, then nothing.
Yeah, but the Russian government doesn't control the people on this side of the line, and. It's kind of it gets down to the user activated.
Yeah, okay. That's just.
Well, no, it gets down to the user activated software stuff. One, you can't compel these guys to propagate. If there's a block flooding attack, you can't compel these guys to propagate things. You could convince them to propagate it. The network protocol has certain rules that say, it says, for instance, when you've been convinced something's the longest chain, one of the things we do is like, well, if someone gives you other things, that's okay, you can make a note of it, but don't forward it until you're convinced it is the longest chain. So, like, okay, so they decide to attack the network, and these guys are like, well, I've got a really profitable thing going on, because it's profitable for everyone. What's going to happen? Well, these guys are going to stop sending them money. The cost of the attack goes up, and we're basically forced to the position that there's a cost to the attack. There's more advanced stuff where, as I said, we can make the cost exponential, but I mean, those techniques are weaker if this guy decides to attack. They're very effective if you have someone who...
you have some random person
who tries to pretend.
I mean, that I think is pretty clear, is that if you like somebody on a shoot trying to come in, it's really hard.
But I mean, this is like Bitmain, well, what if Bitmain starts randomly forking stuff? What, in the Bitcoin proof of work, it's like, what percentage of the network can support them? As soon as you hit 50%, you're screwed. With this, there's actually no 51% attack, because it doesn't matter if you do 51% of the work. And like the mining system, let's say you've rigged it so you've got enough. Let's say you do 80% of the work, and you've rigged the mining system well enough that you can get 51% back. If you've done 51% of the work and you're getting paid 51%, you're still losing 49% of the cost of the block every block. And, honestly, in that situation, one of the major differences is the 51% attack is incentivized, because the people doing the attack are making money. In this system, the people that are doing the attack are losing 49% of the cost of block production.
So, I mean, that's pretty much your attack need to actually be making 50% from like exchange or something.
I mean, I don't even know.
I mean, like I sent $1 million and then I recovered the...
But that's, it's like Bitcoin. One of the, and what is that? That's it's a transfer of money to everyone else in the network if you do that. So it may be that every now and then someone will attack the network, and the other nodes in the network will be okay with it, because if they need to spend so much money, it's a transfer to everyone else. The network's down for an hour, but they had to spend $5 million to get the money to do that.
The question is, can the exchange pretty much notice this and not confirm the transaction? I mean, that's the main problem. I went to exchange and sold 10 million of Saito, and then everybody got paid in the network.
That's any blockchain, because you've got a cost of attack. Like
it is
it's not a
blockchain.
I mean, what I'm saying is, like, look at there are a bunch of vulnerabilities and attacks that people...
So my question is mostly like, do people see the cost of attack clearly just by observing as a node, can I tell what is the current cost of attack?
Well, this is the nice thing. Paysplit is a public variable that's visible in consensus code. So there are things like in Bitcoin mining, who's got the hash power? I don't know. And like another thing with proof of work that nobody talks about, I've heard Craig Wright say it once. He says, well, when Moore's law ends, we may have a problem. Bitcoin security, it is transaction fee volume, but it is in addition to that, because they've got mining as a difficulty function, it's the supply curve of hash power. Because as soon as I can rent 51% of the hash for less than 100% of the transaction volume, I've got a fee recycling attack in Bitcoin. I rent the hash, I produce it. The only question is, how do you disguise it, right? But and also proof of stake, you can think, well, it's all about staking, but who owns the stake, right? How do I know that the network is securely decentralized? How do I know who is attacking the block difficulty production function? In Saito, we don't have this knowledge problem, because everything that's needed to figure out how weak the network is consensus layer public information. So if paysplit's really high, well, and Saito with a paysplit of 1, it's kind of like a version of Bitcoin where the block producers get their money out first, right? Because Saito with a paysplit of 1, the miners are the only ones that can attack the chain. But the miners are also like the lottery holders, but they've also got to burn electricity, so an attack still has money, right?
Yeah.
But the block producers still collecting, like the routing nodes don't get paid, and the block producers don't get paid out of the routing portion, but the block producers are still, they're still in competition with each other. So we have even in this broken version of Saito, it's actually better than Bitcoin because you've got an actual way to pay for the network.
Well, I mean, the attack there is having the hash power for the lottery.
Well, no, because the block producers,
block producer and have hash
if
power.
the block producers get their payment for that block,
Yeah.
the miners can't do anything about the block producer payment.
Well, that's what I'm saying. You have your block producer and the lottery.
Yeah, I mean, it's like any blockchain. If you can do 100% of the work, you can attack. The difference is 100% of the work is a lot more secure than 51%. Also note that in Saito, like in Bitcoin, we've basically got, okay, the way to attack the network is to become really good at mining. In Saito, you've got one function, which is block production. Now, what that means is it means you want to be specializing in massive industrial computing.
Multiple
Right,
different.
like we've got a mining lottery function which is rewarding a different kind of economic activity. But the third one is also, there's basically three actors. There's also the users, because the user transaction flows coming into the system are also a security function. Like if the users see anyone misbehaving, they can democratically vote transaction by transaction to
switch to other parties.
Yeah, and I mean in dynamic paysplit, users can also start moving around the paysplit. So it can be things like if the network comes under attack and it looks like someone's going to protect it, if it looks like it's a routing node, in the dynamic version of Saito, the paysplit can actually dynamically increase because everyone but the attacker is concerned about the attacker. Likewise, if you have centralization of mining and we're really concerned about Bitmain, the network can be like, we're more secure if we pay more for routing.
Yeah.
And one of the really interesting things about this, I don't like going on, but I love Saito. If you think about like Vitalik, and then people are talking about the scalability trilemma. Well, the scalability trilemma says there's an optimal point of network spending for security, decentralization, and scaling, I think it is. If you think about Saito and you think about the way it works, you realize that's entirely wrong because security is subjective to your position in the network. And what you can have in Saito is you can have a situation where moving the paysplit to 0.4 provides an increase in decentralization and an increase in security and an increase in basically the throughput of the network.
Because you're incentivizing
Because we're concerned about miners attacking the network. If we're concerned about full nodes attacking the network, we can increase security by pushing things back. As soon as basically the security trilemma comes, it flows out of any network where you give all of the money to the block producer. If you do that, you've got the problem. In this situation, you don't, because like you can think of this mining in some ways as if you pay miners more, the network becomes more expensive to attack up until the point the miners themselves become the threat.
Yeah.
If you move it down, the network, if the miners are a threat, moving it down increases security, but it's also paying the nodes that are running the network. And it's paying routing nodes, it's increasing decentralization, and it's also making bandwidth cheaper. Because if the routing nodes make more money...
Make more money is avoiding to propagate.
So people don't think about that. It's partly because people are trapped in like the traditional blockchain world where we've decided to give all of the money to the person that produces the blocks, and we've decided that the problem is how do we make this process difficult and ungameable? And what Saito does is says, well, look, that's not the problem. The problem is we know that you're spending money to produce blocks. You can mining and staking. You're dressing up the fact it's money, and that's why those systems are vulnerable because they're dealing with like validators and all sorts of collusion within the network. They're not worried about the flow of fees in, which is what they should be worried about. Like as soon as Infura monetizes, it's over. Saito says, look, that's the world we live in. It's just money. If we have this abstract system where it's just money, we can make it secure by preventing people from monopolizing, and the security challenge is different. money makes it difficult regardless. We just need to make sure that people can't.
Yeah, we need to
Can't
balance
get
it off. Alright.
Anyway, thank you for.
Yeah,
all
thank
the
you
time.
for explaining. Yeah,
Yeah.
so good. Learned a lot. Alright.
Okay, thank you, Leah.
Thank you.
Thank you for watching too.
Thanks.
Nothing but-